All right. So thank you, Lucy, and thank you, IT4I, for making this possible. And welcome everybody to the first presentation. So during the morning, we're gonna discuss a number of presentations concerning code modules and physics being added, while in the afternoon today and also tomorrow, including the morning of tomorrow, we're going to be facing all the hands-on sessions. So you're welcome to ask questions and also to submit your request to the development team. So welcome to gPLUTO. Here is a list of people involved in the development process that are also present during this workshop: Marco Rossazza, Stefano Truzzi, Vittoria Berta, Alessio Suriano, Matteo Bugli, and Giancarlo Mattia. I hope I did not forget anybody. So first of all, you are curious to know about the current status, I guess. What I can tell you is that the standard version of the PLUTO code, I mean the old one you were used to be, will be maintained, although it will no longer receive any major upgrade in the future, because all our efforts are now going into the next version. In fact, in order to efficiently exploit all the new exa-scale computing resources, which are made by heterogeneous architectural complexity, a drastic redesign and an extensive re-engineering of the code was necessary. This also allowed us to engage with new computational solutions and adopt innovative programming models. So the next line of development will be gPLUTO from now on. I mean, both code will be maintained, but gPLUTO will be the only one receiving major upgrades in the future. So what is gPLUTO? gPLUTO is a full rewrite of the PLUTO code, but now targeting the new exa-scale facilities and new generation hardware. It is written in C++, but it also employs some high-level directive-based programming models, such as OpenACC and OpenMP, to provide acceleration when GPU are available. Keep in mind that gPLUTO is not meant to run just on GPU. It can run also on CPU, but in addition to that, it provides support for GPUs, both NVIDIA and not NVIDIA. So we started these activities back in 2020 with the full code rewrite and some support from NVIDIA specialists, except for a number of kernels such as initialization, I/O, user interface, which remained essentially the same. Now, the aim of this kind of action was an exhaustive porting of the code to GPU, of course, but so targeting exa-scale facilities, including both CPUs and GPUs of new generation, but also a complete code revision, since PLUTO is anyway 18 years old, and actually was a good opportunity for us to remodel the code according to more up-to-date needs. Now, I should say that this work is largely supported by the SPACE project. SPACE is a center of excellence funded by the Euro-HPC joint undertaking, which aims at preparing astrophysical codes for the transition to exa-scale. The Center of Excellence has one main objective, which is that of preparing 7 of the existing state-of-the-art European code for the transition to exa-scale on a Euro-HPC facility. Of course, PLUTO is one of the 7 code. SPACE is like a joint effort which involves co-design activities that brings together scientists, code developers, high-performance computing experts, hardware manufacturers, and software developers. Here on the right, you can see a panel showing all the logos of the partners involved. There are essentially 8 different countries and approximately 15 different partners coming from research institutes, supercomputing centers, and HPC companies. Let me show you a brief of history of how we started all of this. So the code was rewritten literally from scratch. We started with a simple mini app, which was including a very simple Cartesian 2D version of the code, featuring just a hydro module with a very simple algorithm. And then that kind of skeleton allow us to additionally incrementally add new modules as time was passing by. So during this process, we added a lot of functionalities, and we also made many small, not invasive changes to adapt the code to new parallel approach. At some point in the timeline, we decided to switch to C++ in order to take advantage of some features, mainly templates, classes, and in some cases, vectors. Also, the reason for switching to C++ was to make a easier handling of index ordering of multidimensional arrays and memory collections, as I will briefly recap in a couple of slides. So you can access the code from exactly the same web page as usual. So both codes actually can be downloaded from the same web page. Just two different links. You should click on download if you want to download the standard version of the code. I mean the standard CPU PLUTO. Otherwise, you need to go to follow the link of gPLUTO to download through GitLab the version 0.85 the code. It's still a beta version, but it's quite functional. And just to let you know, we are already using the code to do scientific production runs. Of course, I recommend before downloading to check if your simulation demands are satisfied by the code, since gPLUTO already contains a number of algorithm and physical modules, but not all of them. So actually, indeed, I'm going to describe what's in the code and what's planned and what is not planned to be ported. So let's start, in fact, from the physics modularity. Okay, at the moment, there were 5 modules in the old version. The last one, relativistic non-ideal MHD, was released upon condition because it was not, let's say, so user-friendly, so to speak. But by the way, all 5 modules have been translated to gPLUTO and are available. The last one is still, I think, upon condition, but will be made officially public in a few months. So the 5 modules, so to recap, are the Euler equation, MHD for magnetohydrodynamics, and then we have the 2 corresponding relativistic extension, RHD and RMHD, and finally the relativistic non-ideal MHD, which include resistivity by incorporating the Ampere's law with a finite conductivity. Now, dissipation physics is the only module that is not being ported yet, although we have one person in charge of it that should complete the work by, let's say, June 2026. We plan to port all 4, actually, even bipolar diffusion will be included. The work has started, but I mean, we are in the very early stage of this. Concerning the equation of state and thermodynamics, we have ported ideal and isothermal and the CNG gas for relativistic flow. We have also planned to port more complicated equation of state, including cooling, such as the PVT law, but at the moment is not our priority. So you are going to have to wait a little bit, or you can code it yourself by following some typical templates guidelines. Cooling is a little bit behind schedule. We have partially ported a tabulated cooling, although we are working on SNEC and MINEC. SNEC is planned. MINEC, I'm not sure about because we don't have so many requests from people requiring this complex network of ionization. Particles. So particles are being ported. So Lagrangian particles are already present in the new version of the code, while cosmic rays is an ongoing activity, and dust particles will follow immediately after. So they are all planned activities. Concerning the algorithms, now, time stepping is present just using Runge-Kutta time stepping, both second, third, and fourth order, although we have no plan to port Hancock or characteristic tracing because those algorithms are actually requiring a complex stencil and we prefer not to use them. Also, the other reason is that gPLUTO will also go in the direction of high order schemes and none of them, Hancock and characteristic tracing, can make this reachable in an easy way. So that's why we essentially took those algorithms out of the development in gPLUTO. So they will not be present in the future. Now, reconstruction. Well, all the reconstruction methods have been incorporated. There are linear, parabolic, Ueno 3, Ueno 5. monotonicity preserving, also the limo tree. So all of them are there. Linear reconstruction also comes with all the available limiters, such as Van Leer, MC, MinMod, Van Albada, etc. Most of all Riemann solvers have all been ported, including to Shock when present, Rho, Lux Friedrichs, all the HLL family, and the G4 scheme. We have also implemented a solid strategy for fourth order finite volume method, which is spread in the code. Is not yet public because there are a couple of things we would like to address in the future to make the module even more robust than the way it is now. Although Vittoria Berta, for example, is using the module for her high order simulation of magnetic reconnection in 3D. We have ported all the strategy to control the divergence of B, including 8-wave Powell scheme, generalized Lagrange multiplier, and constraint transport method. A new feature is the Poisson solver. We do have a Poisson solver in gPLUTO that was not present officially in the earlier code version. The module actually still needs some tuning because we are facing some problem with MPI. But most likely this is due a bug, so we're going to address this issue in the near future. But the module is there. I mean, it's going to be public very soon. We have recently also added support for Fargo, which is a fast advection scheme for rotating objects, a very useful scheme to overcome the time step limitation in Keplerian disk. We are also, well, there is no shearing box model, although some effort in this direction is planned. So let me briefly recap also other features such as the grid. So we are supporting all three geometries now. That was not true a few months ago, but it is true now. So we have Cartesian, cylindrical, and spherical geometry. Non-uniform grid are done using a completely different method from the earlier PLUTO. So the earlier PLUTO has fixed grid transformation that you were able to specify in your Pluto.ini by inserting all the patches, either uniform, stretch, or logarithm. But in gPLUTO, we use a way more general approach that makes usage of mapped grid. So you can define any grid you want by providing a mathematical transformation between a logical space and the physical space. Adaptive mesh refinement. So this is a complex topic. What I can say is that the old PLUTO, as you know, was relying on the Chombo library. However, in gPLUTO, we have an independent effort from David Mellon-Fuchsman to develop our own inbuilt adaptive mesh refinement. There's going to be a talk later on during this morning. Output format are all compatible, so VTK, binary, and HDF5. VTK is being slightly readjusted for parallel and header writing. We support also restart from binary file or HDF5, and we can also allow the input data, I mean the possibility to start the simulation from externally produced data files. Parallel communication can be done either in a synchronous or an asynchronous way. Actually, the asynchronous way is a new feature in gPLUTO that was not present in the earlier version, which is way more performant when you really do massive parallel runs. So let me recap the structural changes between the two codes. So C and C++, so we moved from C to C++. The old code is not able to run on GPU, while the new code is able to do that. Both of the codes support parallel computation. Adaptive mesh refinement and particle support were present in the old version, but they will come at some point also in the new version. The download was done through a tarball archive file for the old PLUTO, but now you can access gPLUTO using the GitLab repository to the public version. Now, in developing the new code, we also try to guarantee as much as possible backward compatibility. So it's not backward compatible, but let's say, as much as possible, meaning probably 80%, So the problem configuration is still defined using the three usual files. These are the init.c++, which defines the initial condition, boundary, and analysis as usual. Again, the problem header file, which now is named definitions.hpp, and the runtime configuration file, which is almost essentially the same as before. Again, as before, we try to make the configuration setup very simple by using the Python menu. So you can just do export by pointing to the gPLUTO directory, then you will follow with the setup using Python 3, and then you compile the code using make, and then run the code. So this is still essentially the same. Let's see what has been changed. So initial condition, they are done using either the init or the init domain, but while the earlier version of the code had just 3 arguments, now we have one more argument, which is this run config structure. And that is a consequence of the fact that we are trying to minimize the employment of global variables. So in order to suppress all global variables, we introduce a new structure, which is called run config, that has the purpose of holding all the collection of variables such as the gamma US, sound speed, and stuff like that, that are not going to be passed to using standard global variables. I will make more examples later. The problem header files remains essentially unchanged. It's just named HPP instead of .h. And Pluto.ini is also very similar. There is one notable exception, which has to do with the grid generation. So as you remember in the old version, we were providing this one and this u, specifying that we had one patch with a uniform grid extension. Now you don't have to do that anymore in Pluto.ini. You just specify the endpoints, like the leftmost number of points and rightmost point, while the grid will be handled separately in a file that does the grid transformation. So this is way more flexible than before. Other important thing to remember, in Pluto, dynamic memory was done using pointer-to-pointer dynamic allocation, while in gPLUTO, we use C++ template with the strided array, which are again dynamically allocated. So this is essentially how you translate from one code to another when you want to create an array. Another important point, the index ordering. So in PLUTO, this was like KJI, as you remember, where K was the slowest and I was the fastest. But now we use internally handle of these indexes using classes. So you always refer to an array using I, J, K. And that is true for either conservative or primitive variable arrays. It doesn't matter. It's always I, J, K, and V. While in PLUTO, there was a little bit of confusion that was actually introduced to make the code faster and to exploit as much as possible contiguous memory allocation, but you don't need to care about this in gPLUTO. Another important point is the ordering and indexing of staggered arrays, because now the I index, as I will show later, refers to I minus one half rather than I plus one half. Okay, so that's very important to remember. Yeah. Indeed, concerning the half integer notation, each time an array in the code has to refer to an interface value, the convention is different from PLUTO. In PLUTO, IJK or KJI refers to the right interface, while in gPLUTO, the triplet IJK refers to the left interface. So don't get confused when modifying the code. Okay, that's very important to remember when you need to access face or edge-centered quantities. These are not just the staggered fields in constraint transport, but also the fluxes and other quantities that may appear during the code. Let me also do some other general considerations. So we have drastically reduced the usage of global variables. There are no DOM loop macros anymore, but we have improved the employment of the box loop macros throughout the code. We have a completely different way to handle errors and diagnostic. The reason behind this is because on GPU, we strongly discourage to insert print statement inside a vectorized parallel loop because that may compromise the performance of the loop. So what we do now, we collect the error during the kernel without printing them. And then later, if there is any error, it's going to be printed by the CPU only. Okay. Another important thing is that the approach to curvilinear grids is no longer based on non-equidistant geometric centroid. So some credits here. So these are the people that I'm very proud to work with in the team. So Marco Rossazza is also here. He's the OpenACC JDI. Giancarlo Mattia is taking care of the PyPLUTO visualization package, while Matteo Buglio is our general relativity and also GitLab expert. David Melon Fuchsman is involved in developing radiation and also AEMR porting on the new code. Vittoria is working on high order method, resistive relativistic MHD, and also CR particle development. Stefano is taking care of code porting issue, OpenMP optimization, and HPC access in general, while Alessio is working on importing also Lagrangian particle. So this is all on my side. So I will stop sharing and take questions. Okay, so if there are no other questions, I would leave the word to Marco, which is going to present a more in-depth feature of the of GPU programming inside the code. Please go ahead.
Are you seeing my screen?
Yes.
Okay. So hello, I'm Marco Rossazza, and I worked on the GPU porting of PLUTO. So as Andrea said, we call now gPLUTO the new GPU-enabled version of the PLUTO code that I'm presenting here. We're going to discuss the rising principles of GPU computing, the characteristic of OpenACC, that is the tool we've chosen for the GPU enabling. Then we'll briefly describe the process we went through, and finally I will show you some performance and scaling results of the application taken on various HPC clusters. Parallel computing in general involves the employment of parallel hardware to execute multiple instructions simultaneously, and recent widespread adoption of parallel computing can be attributed to the physical and technical limitation faced by sequential computing methods. GPUs have been available and widely used for a long time, but in the past decades have become more programmable and flexible, evolving towards general purpose computing. The desire to exploit the computing potential of GPUs led NVIDIA to develop CUDA in 2006, the first commercial framework for general purpose GPU computing. You can see in the time arrow in the slide how GPUs have evolved, and today the majority of the most powerful supercomputer of the world are GPU based. Just a refresh on what a GPU is. A graphics processing unit is an electronic circuit in a computer and designed to handle graphics and image processing thanks to its parallel structure. A CPU focuses its relatively low number of cores on individual tasks and quick execution of serial operation, while the GPUs has many cores able to execute the same instruction in parallel on different data. These cores are the green square here in the figure. That is a scheme of an NVIDIA GPU with Ampere architecture. These cores are organized in streaming multiprocessors, SMs, which can execute thousands of operations simultaneously. GPUs and CPUs are often called, and I will refer to, as device and host. Two very important words in GPU computing are kernel and thread. A kernel is a portion of the code that runs on the GPU, while a thread is a single stream of program instructions defined in a kernel that runs in parallel with other threads and are mapped into cores. A kernel divides its workload into multiple thread blocks, and each block has a fixed number of independent threads that run simultaneously on the same streaming multiprocessor. and can exchange data through the shared memory. Other valuable resources are registers that are the memory working space of threads, and the number of registers needed by each thread depends on the complexity of the kernel and on the number of live variables. The number of registers and the amount of shared memory required by each thread determines the occupancy of the GPU and affects the performance. OpenSCC is a programming model that allows developers to annotate existing CPU codes with compiler directives called pragmas, indicating which parts of the code should be offloaded to the GPU for execution. OpenSCC is directive-based, high-level, and by adding directives incrementally, developer can optimize critical section of the code without rewriting the entire application, as it was our case. OpenSCC directives in C are specified using the keyword pragma, followed by the ACC sentinel, the directive itself, and the optional clauses. The primary approach for accelerating an application with OpenSCC involves using compute directives to indicate the compiler which regions of the code to port to the device, and this is the case of parallel loop in figure. Often is necessary to use data directives to manage memory. Enter data is the most used data directive in our code. I'm now discussing rapidly some important aspects of GPU computing I found crucial for my work. For gPLUTO performance, the main limiting factor of the GPU acceleration is the movement of data from the CPU to the GPU memory. This is because to grant correct results when going from a portion of the code executed on the device to one run on the host, data have to be updated, potentially wasting the acceleration gained with GPUs. To avoid this, in gPLUTO, we keep things on the GPU as long as possible, don't updating data on the host memory. Another matter that affected the shape of the code is privatization. GPU threads have to execute the same operation on different memory addresses. Otherwise, there can be conflict leading to wrong results. This can be done having arrays with as much dimension as the number of loops in the kernel, as for the array A in figure, or with the private clause as for the array B, which creates a private implicit copy of the array for each thread. Another critical aspect that affected my work is the unique memory path of GPUs, which is connected with performance. In particular, correlation memory access played a key role in gPLUTO optimization. When a thread requires an element of an array, it receives within a single memory transaction a bunch of consecutive elements. If the neighbor thread needs an element sent with this transaction, it can work with it. Otherwise, it has to wait, and we are wasting that resource. Whether or not the situation happens has to do with the ordering of the indexes of multidimensional arrays. In particular, we want the fastest index of the array to be also the index of the innermost parallelized loop, as for the case of the loop I, for the index I in figure, because you can see that the index NV is executed sequentially. In the next slides, I'm going to discuss some important changes we have done to the code during the GPU porting process. Andrea already discussed this, so I'm going fast. In this timeline, I'm reporting some of the major events during this year, so from when we started in 2020 with a mini version of the PLUTO code. From this, we started adding directives and changing the structure of some part of the code for GPU execution. And we arrived to the first gain in performance when we were able to port the whole computational part of the code to GPU. Then we could expand the code, adding modules and algorithms to recover all the parts that make a PLUTO, or almost. Throughout this, we made important changes to the code, the most important one being the passage to C++. And then we tested the application, of course, on many HPC cluster, amongst the most powerful in Europe, especially since we joined the space project. In this figure, you can see one of the first adaptation we had to make to start the GPU porting. PLUTO was characterized by very big and complex loops with many nested routines, efficient for CPU execution. We split these type of constructs, creating many more and simple kernels, and basically every routine now as such as the reconstruction, the Riemann solver, and the right-hand side, as you can see, are single kernels. These, apart from efficiency, made our initial work easier because we could accelerate one function at a time. In this figure, you can also see the introduction of C++ classes for multidimensional arrays that I'm describing in a moment. gPLUTO inherited the method for array allocation from PLUTO. For example, memory allocation for a 4-dimensional array is done in multiple steps, as reported on the left. We decided to change this approach, going for a single continuous memory allocation with one pointer only, and using class function to translate 4D indexes to a 1D index. In the slide on the right, you see a template class that encapsulates the functionalities of a 4-dimensional array. It offers methods for array allocation, deep copying, value setting, and destruction. At the bottom, you see a 4D array as it appears in the code, with rounded parentheses and indexes very similar to before. The new method reduces the complexity associated with multiple levels of pointer dereferencing, and while both methods can achieve collection memory access, the single continuous block allocation method generally has lower overhead and more flexibility. We recur to another C++ features that are templated function, again to optimize efficiency on GPUs. More in the specific, we used the direction of integration as a templated parameter in many functions, so that a version of the function themselves is compiled for each value of the direction of integration. You can see on the left that dir is the templated, on the right, sorry, is the templated parameter of the HLLD solver in figure, and 3 HLLD solvers are compiled for each value of dir that are idir, jdir, and kdir. This permits to have every arrays whose indexes depends on the value of dir to be known at compile time, as for the array V in the example. This can be of great benefit for optimal memory access of this kind of variable, making them rapidly available to threads in registers. Another significant change regards multi-process communication. When the code runs on many processes, data have to be exchanged to fill points in inter-process boundary zones at every time step. At the beginning of the development of gPLUTO, we renounced to ArrayLib, the library that took care of this part in Pluto, moving to simple data buffers exchanged between processors through MPI send and receive calls. We then rewrote the MPI implementation and changed this approach that required only 6 directions of exchange. The direction refers to the position of the subdomains of the processes in the global domain. For example, in the upper figure are represented 2 directions of exchange, right and left. Now the data exchange requires many more MPI calls and 26 directions of exchange, but these calls are all independent and can be done concurrently. These 26 can be divided in 3 groups that are exchanges along faces, along edges, and along corners, which correspond to different color of the arrow in figure. Moreover, we use synchronous kernels for data buffer copies, and non-blocking MPI calls for communication. This gave us a good improvement in scaling and performance. In the following slides I explain the 26 direction of exchange, representing the neighbor with whom communicates the PLUTO process. We have here then 6 processes that gives data in the faces of their subdomains, 12 processes that gives data in the edges of their subdomains, and finally 8 processes that gives data in their corners. I can finally show you detailed and recent performance and scaling tests. The problem we simulated is the three-dimensional Orson tongue, a well-known benchmark test. The initial conditions are here in the slides, and the numerical method we used are the Runge-Kutta of the third order, the WNZ reconstruction scheme, and the HLD Riemann solver. We used the constraint transport for the control of the magnetic field divergence. On this graph, I report the weak scaling of gPLUTO on 3 different clusters: Leonardo, Mare Nostrum, and Meluxia. On Leonardo, we run on both the accelerated partition called booster and the CPU-only partition called DCGP. On the graph, you can see that the parallel efficiency for each type of architecture, this value is obtained dividing the time of each runs by the time of the run on one node only. You can see that these values remain at about 90%, even going up to 512 nodes on Leonardo Booster. In the table on the right are reported the resolution per node of each cluster that for weak scaling is fixed, so that ideally the execution time should remain constant, increasing the number of nodes. For the same runs of the previous graph, we obtained the performance parameter. The performance is computed multiplying the number of cells and the number of steps done and dividing by the time and the nodes employed. On the right, you can see a table reporting the speed up factor between the runs on Leonardo Booster and the CGP. So it's a GPU to CPU node comparison. You can see that we are around a factor 10 of speed up. A similar comparison could be using GPU and CPU runs both on the booster partition, and these gave a factor of speed up around 30, but this partition is highly specialized for GPUs, and CPUs are not competitive. We are currently developing the OpenMP integration in gPLUTO, which will allow the code to run on AMD GPUs as well, whereas OpenSCC is limited to NVIDIA GPUs. We have already conducted some successful tests on the Lumi cluster, but OpenMP support still needs to be extended to all modules of the code. Another front we're working on is adaptive mesh refinement. As Andrea told you, PLUTO used to rely on Chombo library for parallel computations and on adaptively refined grids. For gPLUTO, it has been decided not to rely on Chombo anymore, and currently David Mellon-Fussman from Heidelberg is working for this addition to the code. We will also try to scale the code to a higher number of nodes, and the 2 most probable candidates for these are Leonardo and Mare Nostrum. So thank you for your attention, and if you have question, I'm happy to answer. Thank you. So if there are no questions, maybe we can proceed with the next presentation.
Okay, thank you, Marco. I think this is my my time to talk. There's a slight change in the program. I will advance to talk on the GRMHD module of the gPLUTO code. So I will talk about the one of the physical modules of gPLUTO, which was not included in the legacy version of PLUTO. the GRMHD module, and which is currently still under development and will soon be part of the gPLUTO official release. So essentially, the rationale for having a GRMHD module is, of course, the ability to model accretion physics onto compound objects. In a nutshell, what we're talking about here is essentially the physics that concerns the central engine of many physical sources, extremely energetic ones, where we know the accretion can be become extremely efficient when we deal with systems with very deep gravitational well, very compact objects, very efficient at converting the gravitational energy into heat, kinetic energy, and radiation, and this provides also the ideal sites for the emission acceleration of particles, emission of non-thermal emission, and for, in presence of magnetic fields, also polarized emission. And of course, when we talk about accretion and particle acceleration and even jet launching, we know that the magnetic field dynamics plays a crucial role, but it has to be included into generalistic framework where we can capture the effects of a curved space-time. So when it comes to the GRMHD framework, so there is a well-established sort of a baseline, which is the result of decades of efforts of the community to essentially develop a pretty well confirmed and solid numerical framework when it comes to ideal general relativistic magnetohydrodynamic, which has to be confirmed by not just the individual groups, but really a communal efforts by the Event Horizon Telescope good comparison projects, and the fact that essentially we can reproduce reliably the accretion flows and the dynamics around black holes or compact objects. And of course, cannot be overstated the importance of GPUs and the fact that accelerating our GRMHD applications, we can achieve unprecedented accuracy and resolutions, and therefore really take a peek into previously undetected and unexplored regimes of the dynamics of the accretion flows. And so, of course, gPLUTO was the perfect chance to add this kind of baseline framework in the new application. So now I will just walk you through some very basic notation that sets the equations that are considered in the GRMHD module. And as you might imagine, the baseline for the GRMHD is the relativistic MHD module already present in PLUTO, which assumes a flat spacetime. And essentially, we are dealing with conservation equations, parabolic equations, where we have primitive quantities which have to be translated into conserved quantities, which are transported by fluxes and can have also source terms in their evolution. So these are, in the RMHD framework, the usual conserved variables in terms of lab frame mass density, momentum density, magnetic fields, and energy density as measured in the lab frame. And then, sorry, I think, oh yeah, sorry. And then we have the fluxes that essentially are still a function of the primitive variables, and source terms which are vanishing in general in Cartesian coordinates, but they can be non-zero when it comes to non-Cartesian coordinates still in a flat space-time. If we now go and allow space-time to be non-flat, that means that we have to start from general mass covariant expression for the mass conservation and for the momentum energy conservation. And these covariant expression of these fundamental conservation laws then can be casted into a more manageable and numerically friendly expression by foliating the four-dimensional space-time into space-like hypersurfaces. So we are selecting a direction for how time flows. We make a choice in terms of specific so-called Euler observer with a specific forward velocity, which then sets how time flows, a specific the shifting with respect to the coordinates represented by the shift vector, and then this induces also a local 3D metric on this 3D space. And this is all encapsulated in how we measure lengths in the four-dimensional space-time, and all these quantities that I mentioned then defines what the metric looks like. If we now manipulate the conservation of energy momentum tensor and the conservation of mass, we basically arrive at a very similar expression for hyperbolic equations for our conserved quantities, but now we have to be to introduce the impact of having a non-flat space-time. That means that we have something very similar to what appears in the relativistic MHD framework, but we have a geometrical factor that has to be included in our conserved quantities. And when it comes to the fluxes associated to these quantities, we have in red what will be there in flat spacetime, and you see the addition of extra factors given by the last function and extra terms introduced by the shift vector. So we had a different combination of conserved and primitive quantities, but essentially the fundamental structure of the equations does not change. And for the source terms, we have now the appearance of source terms that depend on how the metric changes in over space, their gradients. So this is essentially how gravity is included in a covariant manner within the equations, and but also the different coordinates induce source terms, just as is the case for the relativistic MHD framework. So the covariant formulation captures what the relativistic MHD module does and needs to do for non-Cartesian coordinates. And so this is basically represented by the fact that we can recover the Minkowski limit, so the limit of a lapse function, which is a unity, and a null shift vector. We retrieve the GRMHD equations. And in that case, the induced spatial 3D metric tensor describes what in a RMHD framework will be a Cartesian or cylindrical or spherical system coordinates, or whatever kind of coordinates you might want to implement. The fact that we have a covariant formulation now provides a way to simply not care in terms of the form of the equations about this changing matrix of coordinates, even because everything is encapsulated in a self-consistent way by the adoption of a covariant formulation of the equations. And so this comes at the price, of course, of having to deal with components of the vectors, which are not simply the usual so-called orthonormal components, as in which is usually used in the case of flat spacetimes, but we had to deal with upper indices and lower indices that describe the contravariant and the covariant component of vector fields. And as you can see, we have these factors that are set by the 3D spatial metric that allow us to raise and low indices, and also to relate to the usual coordinates that some of you might be more familiar with. The fact that we also adopt covariant or contravariant components depending on the equation means that we essentially, for instance, for when it comes to the in a spherical system of coordinates, we are essentially, for instance, evolving the angular momentum as a conserved quantity. So we, by default, set the conservation of angular momentum in the way that we implement our equations. So let's dive a little bit into what the code looks like when it comes to the extra infrastructures required by the GRMHD module. So the the main object that, of course, one needs to deal with is the metric, the metric that is not just the expressional metric, but also the lapse function and the shift vector that I introduced before. So you can see here in this screenshot the structure where we basically have different members that represent a scalar for the lapse, 3D, 1D, 3-element vectors for the shift vector, and then the metric tensors in their covariant and contravariant components, as well as the square root of the determinant or its inverse, which are quantities that are basically sprinkled all over the quantities that we need to integrate at evolving time. And in this on the right hand side of the slide, you can see an example of blocks implementing different metrics, and you can see that there are these markers that essentially set a compile time, which kind of metric is the code actually dealing with. So in case of, you can have a user-defined metrics, which is something that you might want to do if not other options suits your needs. And this is something that you can deal with in the init cpp file, essentially the same part of the code where one also deals with specific customizable boundary conditions or internal conditions in the domain. But otherwise, you can also make use in the flat space-time case, the usual coordinates, which can be cylindrical or spherical, and you can also actually use just the default Cartesian. Now, in this case, this is a little outdated because now we only the ambiguity between cylindrical and polar has been resolved. So actually, cylindrical, spherical coordinates, or Cartesian is what you might go for in flat spacetimes. And then you have, of course, the blocks where you don't have, for instance, a flat spacetime. And this is the case, for instance, for the Boyle-Link quiz or the Carrot coordinates that allow to describe the space-time work by a black hole, whether it's rotating or non-rotating. And these two coordinates, for instance, differ in how they deal with the event horizon singularity. When it comes to the evolution of quantities, essentially what the metric is needed for is define, first of all, what the surfaces and volumes in the cell look like, because they, of course, depend on the metric itself. And in order to do that, we define and we construct cell by cell at the beginning, once for all, the values of the integrated surfaces and volumes necessary to perform a time integration. And we do that by exploiting the high-order Gaussian quadratures that are, for instance, used in the high-order module that Vittorio will talk about in the upcoming talks. There are also, of course, the metric is crucial to define the primitive variables and how they change and they convert in conserved quantities, and also the fluxes that I showed you in the formulation of the equations. So the metric needs to be there as well. And it's also required in order to perform operations such as lowering and raising indices. So contravariant to covariant, for instance, coordinates of your vector field, to compute dot products, because we still need to know what the metric looks like, and first products. So whatever we have some vectorial operation that deals with covariant and contravariant components, we need to take into account what the metric looks like. So this is where essentially, for instance, these square roots of the determinant of the metric appear when it comes to, for instance, cross products. In terms of what the definitions.hpp look like for the GRMHD module, essentially there is no major change besides the fact that we need to, by default, consider a formal Cartesian structure of the code, just because of the fact that the covariant formulation allows to, by default, allows to reason in terms of the logical coordinates that always are essentially a Cartesian space, and then the metric factors take care of changing the according quantities in the appropriate way. So essentially, the geometry module assumes that the code is intrinsically Cartesian by default, and the information on the metric is instead set by this new macro, the GRMHD, where one can define different choices depending on the needs for the specific run that you wants to do. So let's go to very quickly to a few tests just to essentially validate the implementation. This is a very standard shock tube test where to test the ability of the code to deal with the non-trivial metric. What we did was allow the lapse function to be different than 0, so affecting how time flows, and then allowing the shift vector to be different than 0, essentially inducing a shifting in the coordinates with respect to the box. And then having a non-trivial spatial 3D metric, which essentially shrinks and can warp the length of the grid itself is effectively. And so you can see here now on the right what a standard shock tube version in an RMHD equivalent, but within the code looks like. So we have the a very familiar formation of the discontinuities and interfaces. But when we do that with by tweaking the metric, you see that the final time is different. The coordinates are shifting, and we also have a different size for the x-axis and also for the amplitude of the vector. But when we sort of adjust for all these effects, so the warping of time, the shifting of the coordinates, and the size of the grid, we essentially fall on top of the standard RMHD solution. So the code is able to account consistently for these changes in the metric. And you can see here there are some cases of oscillations. The worst case happens to appear when we do the same test, but with a 3D rotated shock tube. So this is what induces these oscillations at the sharp discontinuities. Otherwise, all the rest is captured very, very well by the code. This is an example of a 1D accretion solution on top of a black hole, and you can see that the code reproduces the standard problem quite well. And then this is a test on essentially a magnetized polished donut, a thick accretion disk around the black hole with a toroidal magnetic field that is essentially aiding and supporting the disk itself. On the left, we have the hydrodynamic solution. On the right, we have the magnetized solution, which is essentially very similar, just changing slightly the coordinates of the disk and the accretion. But in a sense, we have these solutions, and we have the onset of accretion just induced by numerical dissipation. Just a very quick word about the fact that the GRMHD module so far is in the ideal framework, but we plan on going beyond and capture also the effects of dissipation and resistivity, which is then inherently connected to how then particles can be accelerated, for instance, by a magnetic connection, but also how magnetic fields can evolve and be amplified. And so this is just to showcase, for instance, one of the two major numerical framework where this kind of phenomena and processes are dealt with, whether with a kinetic description or with a fluid resistive GRMHD, which is what the module will be soon be able to perform. But the extra step that we also want to implement is the extension of what is so far constant resistivity, something which is relatively simple, to something more physically motivated, essentially something which captured better what kinetic models predict in terms of how dissipation should look like for in reconnecting carbon sheets, for instance. And so this is the so-called effective resistivity prescription that so far has been adapted and tested in a legacy version of PLUTO, will be tested also in gPLUTO as well, and essentially is able to produce quantitatively, not just qualitatively, the reconnection dynamic that we can see in kinetic models, and also reproduce reconnection rates, which are on point in terms of their amplitude. So this is something that the GRMHD module will directly benefit in the future developments. We mentioned Discord, just 10 seconds. If you want to join our Discord server, just go for it. And in there, we'll find many channels. And if you have a problem, you can see that there are users, that are green highlighted. These are developers, so feel free to join and ask us whatever you need in order to solve your problems, or even have suggestions and any kind of ideas to how to improve either the Discord server, but specifically the gPLUTO code. I'll leave you with my conclusions and some other perspective for the GRMHD module. And with that, I thank you for your attention. I'll take any questions, if you mind. Okay, so if there is no question on the chat, as far as I can tell, I will stop my sharing and then call for the next talk.
Hello, everybody. My name is Vittoria Berta. I'm a postdoctoral fellow at the University of Turin in the gPLUTO group. And today I will talk about the fourth order accurate finite volume method, which has been implemented in the PLUTO code, and in particular, which will be soon released in gPLUTO. So, first of all, what are the motivations behind implementation of high order finite volume methods? The modeling of astrophysical plasmas nowadays demands for more and more efficient and accurate numerical schemes for solving the equations of classical and relativistic magnetohydrodynamics. And in particular, fourth order schemes can reach unprecedented performances, overstepping the limits of second order accurate methods. Also, fourth order accurate schemes provide an intrinsic have intrinsic lower dissipation properties and can enhance smooth solutions at much faster rates compared to traditional second order accurate schemes. Also, convergence, numerical convergence is enhanced, resulting in a higher computational efficiency that increases with dimensionality and resolution. We will see this in much details later. So in a nutshell, our fourth order accurate method combines both the strengths of the finite volume formalism, such as robustness in handling shocks, discontinuities, and steep gradients, with techniques inspired by the finite difference formalism, such as the introduction of pointwise reconstructions, resulting in a simple and efficient numerical algorithm. The fourth order accurate method has been implemented in both the CPU and GPU accelerated versions of the PLUTO code. And it also is presented with the fourth order accurate version of the Apuin constraint transport algorithm for preserving the divergence of the magnetic field to zero. So the fourth order accurate model has been implemented in all the classical and relativistic models of the PLUTO code, starting from the classical hydrodynamical one, all the way to the resistive special relativistic magnetohydrodynamical module, making it the first finite volume accurate, fourth order accurate numerical scheme for the solution of the resistive special relativistic magnetohydrodynamical equation based on an implicit-explicit approach. So our target equations include time-dependent hyperbolic systems of equations for the solution of the conservative flow variables. For example, in this case here in the slide, I reported the resistive special relativistic magneto-hydrodynamical system of equations where 11 evolutionary equations are evolved. Here U is an array of conservative quantities with the lab density, momentum, the energy density, magnetic and electric fields. And F of U is a rank 2 tensor, the rows of which represent the fluxes of each component of U. On the right-hand side of these equations are presented any possible source terms present, which in this case are split for computational purposes, as one of these terms is inversely proportional to the plasma resistivity. And typically, astrophysical plasmas have very low plasma resistivity, resulting in this term becoming stiff, which might cause difficulties in the evolutions of simulations. In this case, we need to evolve all 4 Maxwell's equations, so we are left with 2 evolutionary equations, the induction equations for the time evolution of the magnetic field, the Ampere law for the evolution over time of the electric field, and 2 non-evolutionary equations, which are the solenoidal condition for the magnetic field and Gauss theorem for the charge. The evolution of the fluid variables are coupled with those of the electric field by means of Ohm's law. In our models currently, we adopt a simple Ohm's law with a uniform and constant resistivity, but as Matteo just previously mentioned, we're moving forward to also account for non-uniform and non-constant resistivities. We can also retrieve equations in the ideal limit by considering the vanishing electric field in the fluid restraint and by sending the plasma resistivity to 0. In this case, we are left with only 2 equations, as the electric field is no longer an independent quantity. There is no more stiffness, and the electric field can be described as a function of the fluid velocity and of the magnetic field. Then we can also retrieve the classical limit, as it is shown in the slide. The numerical method. So the fourth order accurate method has been implemented in gPLUTO, which is a finite volume, high resolution shock capturing scheme built for integrating systems of conservation laws, like the one presented on the top left, which is numerically discretized by means of Gauss theorem. So the primary quantities that are evolved in the numerical scheme are the volume averages of the conservative quantities. So we say mass, momentum, energy density, magnetic and electric fields, which are represented as volume integrated quantities of a certain pointwise function. Then the numerical fluxes are discretized as surface average quantities. So for example, in this case, we can see that the x component of a given flux along the x direction is discretized as a transverse integral along the y and z directions. So in this equation, we can notice how no change over time of the volume average conservative quantities subsists if there is no net change in the fluxes that are entering or leaving the computational cell. So at the core of the fourth order method, there is the fact that to second order accuracy, pointwise quantities and volume averages are interchangeable, while this is no longer true at fourth order accuracy. So there is the need to introduce Laplacian operators in order to properly recover pointwise quantities up to fourth order accuracies. Laplacian operators are second order accurate discretizations of second order derivatives, which we use to perform the de-averaging operations, which is the one presented here in the orange box, where the pointwise quantity at the center of the cell is retrieved by means of these Laplacian operators starting from the volume average. The stencil of this operation is reported here on the left in this picture, where we can see that we start from the gray volume averages in order to recover the pointwise value, which is the orange dot at the center of the cell. And in order to perform this operation, we need to introduce one layer of ghost zones per direction. After the averaging operation, when we are left with the pointwise conservative quantity, we convert it into the respective primitive ones, which are density, velocity, pressure, magnetic and electric fields. Then we are ready to reconstruct left and right states at a certain interface by means of fifth order pointwise Winozed and MP5 reconstructions. The left and right states are given as input states to the Riemann solver for the computation of pointwise fluxes. And the fourth order method, we can use nearly all Riemann solvers implemented in PLUTO, so starting from the linearized law, all the HLL family, Lax-Friedrichs, G-force, and this is also the case of the resistive module, in which we have the Lax-Friedrichs and the MHLL family. So then, in order to reach fourth order accuracy, we also need to properly integrate the fluxes to fourth order accuracy. So we perform the averaging operation, which is here reported in gray. So the stencil of this operation is always reported in the picture. So we start from the upwind fluxes, which are the orange dots, and we obtain the integrated flux, which is represented by the shaded gray area. Similar considerations also hold in the resistive relativistic MHD method, for which there is also the need to evaluate the contribution from the charge in order to properly evolve the electric field, and we also need to properly integrate this source term by means of the averaging operation. Then solution is advanced over time. In the explicit update, for example, is proper of all the ideal modules, for which the available algorithms are the Runge-Kutta algorithms. So with the fourth order method, you can either use Runge-Kutta 2, 3, or 4, but it's important to notice that only the Runge-Kutta 4 will give you genuine fourth order accuracy. For the resistive relativistic MHD method, instead, the available algorithms include the IMEX schemes, for the implicit explicit integration, and the adaptive Runge-Kutta 4 algorithm, which is the only one that is yielding genuine fourth order accuracy in the resistive method. So in the resistive method, as I said, we also need to perform an implicit integration step to take care of the stiffness. So it's especially needed to properly update the electric field by means of a Newton-Broyden root fiber, which derives the force velocity needed to upgrade the field. Then, as I said, we also have a fourth order accurate formulation of the constraint transport algorithm to properly control the growth of the solenoidal condition of the magnetic field. So in the constraint transport formalism, it's based on the discrete version of Stokes' theorem, as we can see in the top of this slide. There is a formal correspondence between the time variation of the magnetic field, which is evolved as a surface quantity, and the electromotive force evaluated at the edge of this surface. So first of all, we make advantage of this correspondence, and we retrieve the value of the electromotive force at the center of the surface. Here in the slide, we are looking at 4 adjacent computational cells seen from above. So in order to, we need first of all to reconstruct the electromotive force at edges, but then we are left with 4 different electromotive force for a unique edge. So we follow the prescriptions of Mignon and Delzano from 2021, and we use the upwind constraint transfer method, which gives several different averaging techniques in order to retrieve a unique EMF at the edge. And then we compute the line average of the electric field in order to yield fourth order accuracy. Some numerical validations. So Despite the increased complexity of high-order algorithms, reaching fourth-order accuracy results in a net saving of computational resources. In the top panel of this slide, I'm showing you the L1 norm errors as a function of grid resolution, evaluated on the X component of the magnetic field for a set of three-dimensional circularly polarized Alfvén wave tests, where the green line represents the genuine second-order accurate numerical scheme, while in blue and in red are reported two different fourth-order accurate schemes. So as we can see, the numerical accuracy is enhanced, and this results in a net saving of computational time, which can be proved because when considering a certain accuracy, the number of grid points required by the fourth-order method are proportional to the square root of the number of grid points that would be required by a second-order method in order to reach that certain accuracy. So we can demonstrate that the computational time scales as a function of grid resolution and of the dimensionality of the problem, meaning that the fourth-order method becomes a desirable tool when handling extremely complex numerical simulations that would require very high grid resolutions and high dimensionalities, such as three-dimensional problems. Also, the fourth-order method dramatically reduce the numerical dissipation introduced by the scheme, as we can see on the right panel of the slide, where it is plot the decay rate gamma for always for the circularly polarized, for the damping of an Alfvén wave, with the second-order method in green always, and with the fourth-order methods in blue and in red. And as we can see, there are nearly 2 orders of magnitude of difference in the numerical dissipation introduced. Similar considerations also hold for the resistive relativistic numerical scheme, although in this case, the number of grid points that we require in order to reach a certain accuracy is half of that required by the traditional second-order scheme. We also assure robustness with the fourth-order method. At least we assure a comparable robustness with the second-order method, as it is shown in this three-dimensional blast wave problem, where the initial magnetic field is 100 over 4 pi, and the initial pressure gradient is 10 to the 3. This is a very challenging problem also for second-order numerical scheme. We performed many and many more tests, and therefore I encourage you to go read our articles if you're interested in using the fourth-order method. But I just want to conclude this talk with some future perspectives and some conclusions. So the GPU accelerated fourth-order accurate version of this numerical scheme provides enhanced convergence and improved computational efficiency, especially at high resolutions. It reduced numerical dissipation, and it can assure a comparable robustness with the second-order scheme. What's next? We're interested in implementing non-Cartesian geometries, especially cylindrical and spherical ones, and also to implement a formulation of dust modeling with the fluid approach to fourth-order schemes. So I'm glad to take questions if you have, but I'm done. Thank you.
Okay, hello everybody. Can you see my presentation?
Yes, we can see it.
Okay, so I am Alessio Soriano. I am responsible for developing the Lagrangian modules for the PLUTO code to model the non-thermal radiation from the astrophysical sources. So in my presentation, we'll see a bit of the background of why we need a module, a separate module to address this problem. I will talk about the code structure that we implemented, so a bit of a technical overview, also related to the GPU configuration. Then we'll see some tests and performances resulting from the portion procedure, and then we will talk about the current development, which is non-thermal radiation from magnetic reconnection. So in contrast to the shocks acceleration that is now implemented. So, okay, if we like from observational data, we see that magnetized relativistic outflows such as jets, or supernovas, we see a intense non-thermal radiation that ranges from the radio to teraelectronvolt energy. So we wonder what are these processes that produce such intense thermal radiation. There must be like some physical accelerator that brings the thermal particles to non-thermal energies. So there is some microphysical reasoning we have to do. So for instance, how the particles play with the magnetic fields or with the plasma conditions to be accelerated. On top of these, if we want to simulate a large-scale source, such as a jet, for instance, we need a really big simulation. So in the same problem, we have to take into account of the, for instance, Larmor radius of the particles in the magnetic field, which are 10 to the 4 kilometers for the systems we are taking into account, up to kiloparsec, which is the scale of the jet we can observe with the current telescopes. So very different scales. We of course need a hybrid approach to keep in one single computer all of this information. The Lagrangian module comes to play this role. So when I say one Lagrangian particle, we are thinking about an entity which is a Dirac in the physical space, so a Dirac delta. So it's a single point, but as a non-trivial distribution in phase space. So I have a function that tells me that for a given energy bin, I have a given amount of non-thermal particles. These are the physical particles. So every Lagrangian particle, there's like Lagrangian samplers are advected by the fluid, as the Lagrangian name suggests. And when I am away from shocks, for instance, I apply the Fokker-Planck equation. So that tells me that the momenta of the non-thermal particles depend on some source terms that are, in this case, I would consider adiabatic expansions, square terms in the square brackets, and some radiative cooling. We are taking into account synchrotron and inverse Compton from the CMB. When the Lagrangian particle encounters a shock, there is an acceleration prescription that tells me how the spectrum is changed, so how much energy is given to the non-thermal population. We can see in the GIF here on the right, like an example. On the top panel, there is the simulation. So I have a shock. Left in red I have higher density, in the right I have lower density. So a shock will invest this white dot, which is the Lagrangian particle. And the spectrum, which is here below, is updated because energy is given. Afterwards, the magnetic field will play a role in cooling the high energy tail of this distribution. So we need a huge number of particles, like for instance, at least one per cell in the simulation that we do of a jet. And so we need to write a code that is able to deal with a huge number of particles. If somebody of you is familiar with the PLUTO module, so the legacy code Lagrangian module, you know that we use the linked list. Linked list is a very simple way of storing some information, also based on the fact that we need to add and delete particles constantly, because we can inject particles into the simulation. Particles can leave the domain. So we need a dynamic structure. Linked list is very easy in that. So each node of this list is a particle, where a particle is in general composed by a given amount of data. We can, for instance, have the positions, the velocities, the energy spectra. So this is a node of the linked list. In the same node is also stored a pointer to the next node. So if I want to advect all the particles, I have to advect the first particle to see where the next is. So where in the memory is. So I read the pointer and I go to the next part, so I add back that as well. So it's a sequential structure. We want to pass to GPUs, so we need to guarantee parallel access. The linked list do not work. Another important thing that we have to take into account is that GPUs are very efficient calculators. So if I have to inject particles, I cannot, I cannot perform many memory operations, because every memory operation results in a slowdown of the code, results in the bottleneck of the code. So the numerical operations are performed much faster than memory operations. So we have two problems: parallel access and memory allocation. To overcome this, let's think about the Lagrangian particle for a second as only described by a double, which is the position. So we have only the position. I want to store for every particle one single position. To do that, we use chunks of particles. So for instance, let's say I have to store 7 particles. My chunks are space for 4 particles. This is the prescriptive compile time, for instance. Well, will have 2 chunks. So memory operations are done only once at the beginning of the simulation. Of course, the second chunk is not completely full, but it's fine. Like my simulation works just fine. If I have to add 1 particle, or delete, for instance, okay, I don't perform any memory operation. I just reduce the number, the total size, which is just an integer of 1. So the GPU is happy and not touching the memory. Of course, at a certain point, I will have to add maybe more the particles that what I allocate space is for. So I will allocate a new chunk. But you can see that this operation has been done only once. When my space is full. Of course, these chunks will be much bigger, and so comes the fact that I can perform memory operations only sometimes, and the GPU is happy. Okay, a particle, as we said, is not just one position. I have in general velocity, energies, etc. So we created a class which is called particle container that takes allocates for every of the item of the particles the chunks. In this case, I exploit, if you follow Marco's presentation, data locality. So if I have to advect all the particles, all the positions are stored next to each other in memory, and that means that adhesion threads can access adhesion positions in the memory, and this also maximizes performance. In a linked list, all the positions are scattered in the memory, so this results in bottlenecks. Once we created this structure, we test it. For instance, here we evaluated a shock, like a simple shock, the one I showed before, with PLUTO and gPLUTO, and here the steep curve with solid line is the particle spectrum before a shock. The dash line is after a shock, and blue and red colors refer to PLUTO and gPLUTO. So the legacy code and new code, you see that the agreement is perfect. So here is the relative error. If you want, we are 10 to the minus 12, which is machine precision, but that we cannot achieve. On the right, we perform a parallel test, because of course, like parallel communication has been implemented using MPI. So this is a horizontal, it's a chaotic problem, so particles are vectored all around the grid. The red lines are boundaries between processors, and we can see that we don't lose any particles. So when a particle crosses a boundary, is found in the other processor. So this is very important. So yes, this was regarding numerical tests. We come to the speed up. So because all of this has been done to achieve some improvement in the performances, we tested this module on Leonardo, and recently also Mare Nostrum, which is Cineca and DSC computers. So on the left, we see the speed up. This is done up to 256 cores. So I'm comparing one CPU with one GPU. We have a speed up of 65 times. So one CPU, one GPU. If you go on the node, if we evaluate the node speed up, we have a factor of 8. So a Leonardo CPU node compared to a Leonardo GPU node. And note that the speed up of gPLUTO is higher than the speed up of PLUTO. That means that we achieve performances also on the CPU version, because this code can run on CPU, of course, like the code is on GPU, but the fact that we implemented the parallel, contiguous memory for the structure gave us performances also on the CPU version. Regarding the parallel efficiency, we are up to 80% parallel efficiency on GPUs, always on Leonardo, up to 256 now cores. Considering that we haven't yet implemented the asynchronous communication, is a very good result. We plan in the future to, if we see that parallel efficiency is a bottleneck, we plan to implement also parallel asynchronous communication. For now, we are satisfied with the results. And yeah, and also, like, of course, on CPU, the parallel efficiency reaches 90% because the CPUs like suffer less of hangs than in the MBA codes. Okay, some future developments. So we ported the code. The shock framework that was already there is working fine, but we want to add more physics. And I'm talking about magnetic recognition. So as you know, like in astrophysics, we assume ideal plasma, so magnetic topology cannot change in principle, but there are some regions in which there is a finite non-zero resistivity, and this can allow magnetic energy to be dissipated into heat, but also into non-thermal particles. And this is one of the processes that is suggested for explaining the non-thermal features observed in jet. So we studied the peak results, and we find that the power law index of the non-thermal distribution, as well as the efficiency epsilon of the acceleration, depends on the sigma parameter and the beta parameter of the plasma, so magnetization and ratio pressure over magnetic field ratio. So we can implement that. We can let the particles can sample the plasma conditions. For instance, in a current sheet, which is plotted here in a static way. So the current sheet is static. The fluid is not evolved. The particle enters the current sheet, measures sigma and beta, and reproduce, and is updated, reproducing a steeper power law. This is like a simple test. We come to test this new framework implemented with a plasma column. So it's a plasma column going into current-driven instability that develops for regions in which the magnetic energy is dissipated. The Lagrangian particles that are plotted here, this is the density plot, along time, sample sigma and beta. So for instance, let's focus on the magnetization here on the left. At the beginning of the simulation, the magnetization is really high. I have like the energy stored all in the magnetic field. As the time evolves, the magnetic energy is dissipated, so sigma lowers. Same goes for beta, that increases because the pressure, the plasma gets heated and the pressure increases. And this results in a given distribution of power law indexes. At the beginning of the simulation, where I have a lot of magnetic energy that can be dissipated, I have spectral indexes that are around 2. So that is what I expected from the observations. This is the result of the simulation, where on the right I'm plotting the overall power spectrum, so the average power spectrum of all the particles that have been accelerated. And so at the beginning, like orange curve, I have a lot of magnetic energy available. I'm producing a power spectrum which is around, with a spectrum which is around 2 steepness. And as the simulation evolves, more and more particles are injected into the non-thermal population. So this normalization of the curve increases. You can see on the right energy tail that the magnetic field is fueling some cooling. So the tail bends toward lower lower energies, but new, less efficient acceleration are accumulated, and in the end, they produce a broken power law. So with the high energy tail, which is a steeper with respect to the low energy tail. So I have a module which is able to reproduce efficiently a broken power law from magnetic recognition. This has been submitted to review. So we are in the later stages, and it will be soon available in the PLUTO code. So I leave you with my summary, and I am happy to take any questions if there are any. Okay. If there are any other questions, we can proceed with the program that, if I'm correct, include, yeah, it's Giancarlo with PyPLUTO.
Okay, so I guess I can start. Hi everyone, I'm Giancarlo. I am a postdoc at the Max Planck Institute for Astronomy, and now I'm going to show you like PyPLUTO, which is a Python package to load, manipulate, and visualize data from the PLUTO code. So just a quick recap of how the scientific process can work. So we think of a scientific problem, then we construct by our setup with gPLUTO. gPLUTO is a great code, so everything runs without issues or debugging. And then we are left with an output. Then if you try to, for example, to read naively a binary file, you will end up reading this, which is really not user-friendly, right? So we need tools to decipher this output in order to have numbers and subsequently some plots. And if we are lucky, we go back to square one because we solved our problem. And if we are a little bit more unlucky, we go back to step two and we think of a better setup. PLUTO and gPLUTO have a plethora of output formats, and each format comes with pros and cons. So general tools like, for example, Visit, Preview, or YT sometimes struggle to capture all the capabilities of the PLUTO code in this sense. And if you want to choose to pick your best post-processing, let's say, tool to visualize your data, you can start maybe with gnuplot. It's free. It supports a couple of formats. You cannot really do great data analysis. And then you maybe move to Visit because you still want something that you don't have to pay to use. Visit and Paraview are great for 3D volume renderings, but they don't support the PLUTO format, and the data analysis is also limited. You can choose IDL or Mathematica, which supports basically all the format of PLUTO and gPLUTO. You can do a lot of extensive data analysis, but they are not free. So especially for master students, PhD student, young PhD student, that can be an issue. And that's why we have PyPLUTO, which is free, supports all the data formats, and you can do extensive data analysis, as I'm going to show later. So first question, what is PyPLUTO? PyPLUTO is a Python package specifically designed for PLUTO and gPLUTO. Disclaimer is that when we have completely rewritten PyPLUTO in Python 3.10, we ensured retrocompatibility with PLUTO. However, with the new advances of PLUTO, for example, image refinement, we will stick with the GPU accelerated version. We will stick with gPLUTO. We will implement PyPLUTO enhancement for gPLUTO because, as Andrea said before, no major updates of PLUTO are coming. PyPLUTO works on Windows, Linux, and macOS, and we make sure that it's going to stay the same. It's suited for standard scripts, IPython, Jupyter notebooks. It also works on clusters. So the aim is that if there's a place where PyPLUTO should run, it's going to run. The focus of PyPLUTO is beginner users. So it should be a tool designed for people. It is a tool designed for people that have little knowledge of Python and or data visualization. It has strict rules for development because our aim is for PyPLUTO to be users oriented. And so if that makes developers' life a little bit harder, well, so be it. And for the same reason, we have extensive documentation examples. Why PyPLUTO is another question that you may ask. First of all, why Python? Well, there's an easy answer. Python is one of the most used programming languages in the world, especially for beginners. For beginners to programming, Python is a great programming language because it's easier than many other languages. It's also in constant development. Like an example is that now in Python 3.14, there's going to be a massive enhancement on strings, which is something that you wouldn't expect from such a structured and developed programming language. But yeah, here we are. And for the same reason, there are packages for almost every need. So we can rely on the power of a large community in order to have the best compromise between efficiency and ease of use. Now, you can use your own Python scripts, for sure. I mean, I'm never going to complain about it. But as for the same reason, collective improvement is a thing. So we are looking for users to tell us what they would like to have in PyPLUTO. And every user needs, we're trying to implement it so that the community is satisfied and we can all gain from it. Another advantage of relying on PyPLUTO is that it's always going to be in sync with the new gPLUTO updates, and also that it's going to be in constant development. Now, to install PyPLUTO, it's very easy. You go on the folder, gPLUTO folder, tools PyPLUTO. You create your Python or Conda environment, and then you install it with pip. So very easy. If you want to contribute, you have to go on the original PyPLUTO repository, which is where we put the latest advances. But at the same time, you can also contact us directly, and we are gonna take care of it. PyPLUTO is made of mainly 3 classes, and 2 of them are for loading, one for the fluid and one for the particle. You can, of course, customize your which output you wanna load. You can also, for the fluid, load multiple outputs at the same time. The data type, the file format is going to be taken care by PyPLUTO directly if you don't specify anything, but of course you can specify the file if you want something more specific. And you can also select only few variables to be loaded because it's just a little bit faster. The biggest advancement compared to the previous version of PyPLUTO is the memory mapping. So if you have very large data, which is what we're hoping to have with the GPU accelerated code, and we want to, for example, analyze the data on our laptop, there's the big limitation which is dictated by the RAM. With PyPLUTO, this is not an issue because we rely on memory mapping technique. So only the variables and the memory that we are actually using is effectively loaded, which means that I have, if I have a 50 gigabyte file, but I only want to use 2 because I need maybe only 1 variable, but I have the data in single file, that's not going to be a problem. PyPLUTO is compatible with all PLUTO and gPLUTO geometries, dimensions, and format for fluids and particles. Some formats do not actually need the file .out, so we made sure that if by any chance you forgot to have it, if the format allows it, then there's not going to be any problem. And also we have implemented different tools for fluids, like for example, the Nabla operator, Fourier transfer, and for particle analysis, some tools, for example, to compute the spectrum. And the other big class which PyPLUTO is made of is the image, which is aimed at visualizing the data. Now, PyPLUTO right now supports 1D plot and 2D plots for both fluid and particle. It features highly customizable subplots, so you don't have to worry if you have a non-trivial subplot position. PyPLUTO takes care of that almost automatically. Zooms are made very, very easily, as well as field and quarter lines. And we also allow for interactive visualization, so you can actually see your simulation evolving in time. Another very important feature of PyPLUTO is the graphics user interface, which is downloaded and installed as a sub package. So you just have to type PyPLUTO GUI on the terminal. It supports single subplot, 1D and 2D files. For the 3D data, you have to do slices. You can customize your output and your plot in terms of range, levels, color map. Again, supports all PLUTO and gPLUTO formats and geometries. And for now, it works only with single output fluid but we're working in a way that we're going to extend it to particles and also to see the temporal evolution of the simulation. This is an example of the graphics user interface. It has a couple of panels, so you can choose your variables and access. You can exploit the matplotlib commands, which are very useful, so we don't have to reinvent the wheel. It has a small information panel. You can customize range scales, so on and so forth. You can load different data, and then you have, of course, the plot window. PyPLUTO is pretty thoroughly documented. I mean, half of the PyPLUTO code is doc strings and strings that go into the documentation. And for the same reason, we have an extensive set of tests in order to allow users to easily check which is the feature that they need for to produce the plot they want. Now I'm going to show a few examples. The first is how to plot a shock tube with a GUI. So you go in the format. This is still PLUTO, but it's just because the video is a little bit outdated. You can put your title. You can change the variable. You can overplot 1T plots, and this is your favorite shock tube. The GUI also works with 2D data. So this is an orthogonal vortex. You choose the variable to be plotted. You can change, for example, your color scale, set the range. I don't like the color map. Maybe I want it diverging so I can see high and low pressure. And here we are, and you update the plot. As you can see, like very, very easy, only buttons. That's the aim of the graphics user interface. Let's go a little bit more into like scripting, because GUI is amazing, but sometimes you require like more sophisticated plot for your scientific paper. This is rotor test, so non-Cartesian coordinates, and this is a pseudocode. I'm going to show now mostly like pseudocodes. You load the data, you create the image, you display the 2D data, you put the contour lines, and you save the image, or you show it. As you see, very few lines of code. Field lines are a little bit trickier, but this is not a PyPLUTO issue. This is actually a matplotlib issue. If you know that with streamplot, well, I feel very sorry for you. If you don't know it, well, just bear in mind that PyPLUTO takes care of it with just like 2-3 more lines of code. Another test, you can perform Rayleigh-Taylor with field lines. Again, this is a more complicated figure. It has 3 subplots plus a color bar at the right, but you see the number of lines doesn't really increase. You have to loop in order to plot different output efficiently. Display your 2D plot and you stream plot your field lines, and then at the end you plot the color bar, but this is basically it. Okay, maybe this is more complicated. So we have 2 inset zooms and 1 with a different variable. No, not really. I mean, you still need roughly the same lines of code. You load the data, you create the image. Here you create the axis because you have 2 zooms. Plot the 2D data, first zoom, second zoom, to save. Okay, this is interactive. This is the temporal evolution. So maybe this will need a lot of lines of code. No, not really. It needs literally like 5 or a little bit more depending on your code formatter. This is literally what you have to do. You load the image class, you write interactive, and then you see the data. You can load more than 100 files at the same time, even if they exceed the RAM because of the memory mapping technique. Right now, it's only available for the fluid. Soon, in the next releases, we'll also like take care of the particles. Speaking of particles, maybe this requires a little bit more lines of code because it has also like another plot inside the major subplot. Yes, this finally requires, let's say, around 10 lines because you have to load the fluid, you have to load the particles. Here you should, for this plot, we also ordered the number of particles, basically because this is 412 squared with 4 particles per cell. So there's a lot of particles, and we wanted to show the most energetic ones. This is the Lorentz factor. For this reason, we had to order the particles depending on the Lorentz factor. Otherwise, the high energetic particle will be completely covered by the low energetic particle. But this is mostly because the simulation has a lot of particles. You contour the vector potential if you want to see the X-point region. Plot the particles to scatter. You create the other axis. You compute the particle spectrum. You plot it. And this is literally the end of story. So if you're still not convinced that you should transit to PyPLUTO, I want to show some examples from collaborators and also PLUTO developers. You have seen Alessio Suriano giving the previous talk. This is plot from paper published in 2023, 2024. David Mellon-Fuchsman, person that like a developer that is developing the AMR for gPLUTO, Vittoria Berta, high order, Matteo Bugli, GR. Eleonora Puzzoni was a former PhD student of Andrea Mignone. This is a turbulent simulation. She's also a collaborator for PyPLUTO. Again, Vittoria Berta, this is a plot for magnetic, her production runs on magnetic reconnection. A paper that I want to write on bipolar diffusion, first PLUTO, then gPLUTO. And for this, I actually didn't run a gPLUTO simulation, but this is also to show that the image class is code independent. And if you want to do some preliminary analysis or compare, for example, your gPLUTO with some post-processing thing, you can still use PyPLUTO. It's tailored for the PLUTO code, which is awesome, but at the same time, it also provides like a very broad comfort zone. And these are also other papers that use PyPLUTO in both their alpha, beta, and published version. And if you're still not satisfied, PyPLUTO is not only great for scientific publication, but also for presentation. These are a couple of videos that we produced through the years. We have chats, we have reconnection, we have turbulence, we have multiple subplots, customizable color maps. So there's literally like everything you need. So in conclusion, in the present, PyPLUTO provides easy and efficient loading, all formats, access customization, field contour lines, graphic user interface. And in the future, we're aiming for even more efficiency. So if we can save significant time while doing our post-process and doing our data analysis, that would be awesome. Our big effort is going to be in improving the graphic user interface, because that saves also a lot of time. But this is more in the late future. We're going to put our focus on 3D plots. We have a paper on Journal of Open Source Software, which was published between Tuesday and Wednesday. This is the QR code, and if you have any questions, please contact us. We are very happy to interact with the user in order to make PyPLUTO better. Thank you.
Okay, so good afternoon, everybody. So the afternoon session will be conducted by me and Vittoria to start with, and then following we'll do the hands-on session. So don't worry if we cannot cover everything today. So the plan is to start with the talk with Vittoria, showing very briefly what are the main elements for migrating one setup from the old code to the new one. And then I will do a real-time interaction session by showing what I'm doing on the terminal, so that you can actually understand what has to be done to port one setup. So Vittoria, please, you can go ahead and share your slides, and I'll follow immediately after that.
So welcome back, everyone, to this afternoon session. So I will start with a simple presentation showing some of the main aspects in migrating from PLUTO to gPLUTO. So I want to collect some of the most critical aspects in this migration, but feel free to then ask us all the questions you might have if you already tried to migrate your setups, etc. And there's also going to be the live coding to show concrete examples of this. So the step one is downloading gPLUTO. So there are several possibilities, including mirrors. One of them is from IT for AI, but most importantly, the public version of gPLUTO can be downloaded on the GitLab repository. So step one, you go to the PLUTO code astrophysical website, which is the same one from which you can download the past versions of the PLUTO legacy code. Then you go to the PLUTO GPU section, and you will find a link to the GitLab repository. And from there, you will be directed to the free gPLUTO repository, from which you can clone the distribution and download the code. After setting up your environment, first recommendation, heads up PLUTO users, gPLUTO has the same GUI of PLUTO, but if you're still planning to use PLUTO while using gPLUTO, remember to export the correct environment variables before starting. So remember to export the correct PLUTO directory before starting, or otherwise you might make some confusing compilations and errors and things like that. After that, as I said, PLUTO has the same GUI of gPLUTO has the same GUI of PLUTO. So when you invoke the Python setup, you will find pretty much the same screen that you are used to with PLUTO. A little bit different is for makefiles, because then you will be asked to select the specific makefile that you want. So .acc extensions are meant for GPUs. You might also find some makefiles with .nvtx extensions, which enable the NVIDIA Toolkit extension library. But this is not something that can be of, I mean, it's not required, can help you simplify your profiling, but NVTX extension does not give you GPU support. So if you want to run your code on GPUs, you will have to select the .acc extensions. So in this table, I summarize the main makefiles that you might want to choose. So if you want to compile your code and run it with a single CPU, you will select G++ or MVC++ configuration files. If you want to run on a single GPU, the correct makefile is the nvc++.acc.defs. If you want to compile in parallel for parallel CPU computations, you have the MPI cxx.defs, while for GPUs, you will have the MPI cxx.acc.defs. So just thumbs rule, remember that .acc is for GPU computation. Okay, so you might encounter some issues when compiling your code. This can happen or might not happen. This is because different GPU-enabled hardwares might manage memory differently. So you might notice that on some hardware, your application is compiling correctly, where on some others it might give you this particular error, which is related to memory manage. As you can see, there is the use CUDA manage memory in the screenshot. So if this happens to you, just no worry. If you encounter this problem, you just go back to the config directory. You select the makefile that you're using, and you search for C flags and LD flags. In this case, you will find that there are certain areas which treat the way memory is managed. So you either remove or add the mem. And so you might have mem managed or either managed, and you try to compile again. So in almost all the cases, this is simply going to fix this problem. Just mind this whenever you're changing hardware, depending on the type of hardware, you might have to add it or remove it. Step 3, running gPLUTO. So you can run gPLUTO with the same command of PLUTO. So there is no difference, PLUTO users. It's always /PLUTO for serial CPU or GPU computing. While for parallel CPU or GPU computing, you can use the MPI run command or srun, depending on the cluster or the infrastructure you're running on. Now, let's take a little bit of a deeper look in the most important files. So first of all, the output log files that you will get. You will notice that gPLUTO log files yield more detailed outputs. So on the left, there is gPLUTO, while on the right, there is PLUTO. As we can see now, in gPLUTO, we're printing also the maximum and minimum values of the primitive quantities in your simulation. So here, for example, in the first column, you're looking at the maximum and minimum volume of density. Here there are 3 components of velocity. You might have pressure. Depending on the module you're simulating with, you might have several variables or some others. But it's a richer output. Now, let's see the definitions.hpp file. So first of all, the extension is now .hpp, but the file has not changed overall. The only addition is the introduction of the migrate feature, you can see here. So this feature is enabling or disabling the migrate functionality, and when it is deactivated, you're running with a simple uniform grid. Also, the PLUTO.ini file is overall identical, except for the grid section, as we have removed information on the grid and on the patches that was present in PLUTO. Now, it's no longer present in gPLUTO, but Andrea later will show you how to properly set a stretch grid and how to handle this type of information. Now, the init.cpp function, it's a little bit different because now there is one more input parameter, which is the run config structure, which helps you initialize all the quantities that you want to be set at runtime. In particular, for example, one of the main changes is that now the gamma index is no longer a global variable, but it's now initialized with the run config structure. So you can initialize all these variables and values in the PLUTO.ini file. When you're not if you're not specifying anything for the gamma and you're using, for example, an ideal equation of state, the code will set it by default depending on the physical module that you're choosing to simulate with. For example, this is another example. All the custom variables that you want to introduce now are initialized always through the run config, with the input parameters no longer global variables, but is now initialized with the run config. For example, in this case, we have this mass of a star in this configuration. Okay. Now, as we said, there has been a consistent revision and redesign of gPLUTO, coming from PLUTO, and this table briefly summarizes what Marco extensively explained to us. So I won't really go through this, but now we have changed the kernel construction, the memory layout of arrays is different, function directionality with the introduction of template functions. Communication is handled differently, and also error diagnostic has to be handled differently due to the nature of GPU computing versus CPU computing. So I just want to give you some do's and don'ts to help you start getting familiar with gPLUTO. So GPU computing offers significant advantages in parallelism, in energy efficiency, in scalability of your given problem. However, it can present some challenges which are related to program complexity or the algorithm adaptation and maintenance of your work, or, for example, hardware heterogeneity, as we saw, for example, with the managed error that you might get, or some unexpected behaviors. So understanding this factor is important to effectively exploit GPU technology. So in this table, I presented such do's and don'ts as a guideline for what can help you safely migrating from PLUTO to gPLUTO. So first of all, after downloading your code and setting your environment, read the user guide and the change file, which is present in every distribution of the code, where a summarize of the most relevant changes from one version to the other are presented. But most importantly, read the user guide, because most likely you will find there all the information that you need to make your changes or to exploit the new features that we are providing. So strongly encourage, read the user guide, first of all. Then port your application and do not get discouraged if your application does not immediately gain performance. So we're going to come back on this, but it's important to stress out that GPU computing, the fact that you're running an application on GPUs does not immediately imply the fact that you're observing a speed up in your application. So it is really important to not get discouraged if you see your application running with gPLUTO and you're like, oh, this is not really speeding up. What am I doing wrong? There is some more steps to take and some more understanding behind this. In fact, it is very important to understand your hardware capabilities. Do not assume that all hardwares are the same and behave the same, because this is where you might encounter slowdowns or not observing the speed up that you want. Then, one thing that is strongly encouraged but is not really necessary or required is to profile your application in order to find where are the bottlenecks of your problems and your applications. And also, I strongly encourage you to participate to GPU hackathons or summer schools that are talking about GPU technology and how to use this new these new tools. So here at the bottom of the slide, I put some useful links that you will find. For example, beside the user guide, you might find all the complete and technical information on gPLUTO can be found also in Marco Rosazza's PhD thesis. For those of you especially interested in GPU technology and if they want to really understand what's behind the porting of gPLUTO, I encourage you to read this thesis. It's publicly available at this website. Then I also encourage you to participate to hackathons in Europe and also to schools. For example, Chineka is organizing schools, but there are also many other appointments, and you might find some of them here. I link the website of OpenACC, but you might find them also online. And also, I'll get back later on this, but I strongly encourage you also to join our gPLUTO Discord channel, where you can post your problems or you can help other people who might have problems. So we are a spreading community. Okay, just going a little bit more into details. You will see this in the live coding that Andrea is doing after my talk. So very important to port your applications. PLUTO comes with a set of test problems from which you can take inspiration for your needs. But sometimes you might want to have you might want to use some user-provided functions, for example, the use of user-def boundary conditions, or you might want to enable an analysis function, you might want to use a body force, etc., in your problem. And these functions should be correctly ported on GPUs in order to have performance. So depending on what you have to do, you might need to include some clauses. For example, in this case, I put a snapshot of a reduction clauses when you are for example, to integrate some data or to enter some data from the GPU and then not forget to delete it. So this really depends on your on what you have to do on your applications, and we will see examples of it. We provide a lot of examples in the test problems, so you're not you don't have to invent anything. Then, as I said, profiling is recommended to optimize the performance and accelerate your applications. There are many profilers available on the market. I won't spend too much time on this. So they depend on your hardware, on the software. For example, I suggest the NVIDIA Insight system. But most importantly, as I said, is important to understand your hardware. So I want to stress this another time. the GPU speed up is a regime. So speed up is not automatically achieved by running your applications on GPU. So do not expect to take your application from PLUTO to gPLUTO and magically see it speeding up, because it requires proper exploitation of the hardware capabilities. And that depends on the GPU type, on the system architecture, etc., etc. Also on your problem. So you won't get the same speed up on different hardwares. What I put here to survive to all of this, and as I know that most of us are also interested in making their own science and applications, so I would say the thumb rule is that you are in a speed up regime when approximately 80 to 90% of the GPU memory is saturated. So how to understand this? Let's suppose that you are running your application on a certain cluster on GPUs. So you start your application maybe for 100 or 200 steps. And while running the application, you log in on a working node and you type NVIDIA SMI command. And you will notice that this window will pop up on your screen with a lot of useful information. Most importantly, here you will see the power consumed by the single GPU. For example, in this example, I'm using two GPUs. So you can see that the top line is the first one with index 0, and the second one is with index 1. So for example, here it says the power consumed by the single GPU. Here you find the memory percentage used by the single GPU. So in this case, I'm properly exploiting the GPU. And here you'll find the memory used by the single GPU. So you kind of want these numbers to be above 80%. Okay, just a quick recap of how to safely migrate. So first of all, download gPLUTO and set your environment correctly by exporting the correct variables and paths, and by downloading correctly or the compilers that you need. Read the user guide to migrate and to adapt all the prototypes from old PLUTO to new gPLUTO. Then port your applications, especially if you have user-def functions. Says in general, the init.cpp function is already okay. It's already ported, so you don't have to do anything. But if you add some user-def functions, you might want to port them on GPUs. Otherwise, they might become bottlenecks of your applications. And then it's very important to understand what's your hardware's capability, whether you are exploiting or not the GPU fully, and adjust it consequently. Maybe you want to change the resolution, maybe you will need to adjust the number of GPUs that you will use, etc. Optional, but recommended. Profile your application to understand all of this. And if you have issues, you can always contact us on Discord. In fact, now gPLUTO has a Discord channel. So on this QR code, if you scan it, you can enter the Discord channel of PLUTO, where we will be happy to support you with your problems, and you might find help also from other PLUTO users. So thank you so much. This is all I wanted to say.
All right, thank you, Vittoria. If there are questions, even the dummy ones, no problem. We are actually here for this reason.
Exactly.
Yeah, I can also tell you that on the PLUTO website, I'm going to share my screen so that you can see it. Right. So if you go on the PLUTO website here, under gPLUTO, okay, so that's a home, just go on gPLUTO. And at the very end, there is a PDF document, which is the main one that we'll be using throughout the practice session. So that's the first presentation you can download, because we will follow these slides quite a bit during the following hours, and especially tomorrow. That's the first one. And the other presentation will be made available to Lucy during the next days, of course.
Perfect. Thank you.
Okay, no problem. So, right. So Vittoria gave quite a detailed view of how the code can be configured and set up. So I will make an example, a practical example by sharing the screen again, but this time without any presentation, but by just working out really on the terminal and see how you can manage to do this, okay? So you should be able to see my screen where you should see a blue terminal and a yellow one. Just hold on and give people writing to me. Okay, right. Right. So the idea is very simple. The blue terminal will be used for PLUTO, the yellow terminal for gPLUTO. Okay, so PLUTO on the left, gPLUTO on the right. So the first type I will port is the simple Orson-Tank vortex. Okay, so I'm just gonna switch here, make sure my directory on the left terminal is the old PLUTO. I'm not using GPU, of course. This is just a very simple porting CPU to CPU. Okay, we will discuss GPU usage later. So the first thing, I'm gonna define the environment variable. Okay. And then I'm taking one configuration. I can take, for example, configuration number 3, but I mean, anyone will do the job, okay? Right, so now in PLUTO, I can proceed normally by doing the setup using Python. Okay, so this configuration, again, is for the Orson-Tank. It's an MHD configuration with 2 dimensions in Cartesian coordinates. Doesn't have any body force or cooling. We have linear reconstruction, second order Runge-Kutta. I mean, the very basics. No tracer, no particles, no user-defined parameters. Yeah, then we go to the MHD submenu, where we can select the equation of state, but we can leave the configuration as it is. So ideal constraint transport and leave everything else to no. Actually, I would suggest that everybody does the same thing. I don't know. I mean, this is something you can do on your own laptop. It's not a big deal. Any version of PLUTO starting from 4.3, 4.2 on should work. Okay. So now I have done the setup and I can make regularly. This is PLUTO again, okay? So I'm using GCC as a compiler. I'm on a MacBook Pro, so done. So then I can run the code as usual, and then you will see the standard log file, the percentage, the MAC number, etc., etc. So let's give a few seconds until we hit to the end. So, right, so now we have done this. Okay, now I'm switching to gPLUTO. So the first thing, I'm creating a completely empty directory, which I call TMP, because it's a temporary thing. I want to do everything from scratch. So of course, I've done this in the past. I could just simply show how to do it by showing the code, but I think it's more instructive if I work out by myself, line by line, how this migration can be done quickly. So the first thing I'm doing is that I'm copying all the relevant files. So now I'm back on the PLUTO terminal, the left one, okay? And what I'm doing is to copy the ini.c, definitions.h, and pluto.ini from the Orson-Tank directory of the old code to my temporary directory, okay? Like this. So these 3 files. So now if I ls here, I can see 3 files. First step is just changing the names. So I'm gonna change definition.h into definitions.hppe. And I'm gonna do the same also for init, so which will switch name to init.h. CPP. Right. Then I'm going to open all these files in an editor. Okay, here is my editor. If the fonts are too small, just let me know. Well, I can increase a little bit, but not too much. Okay, so now let's work on my init CPP because I have changed the name, but that doesn't mean that it automatically will work. In fact, there are some adjustments that have to be done. Victoria already discussed some of them. But let's look into detail. So the first thing is changing the name of the header file. Okay, so it's not pluto.h. There is no such thing as pluto.h, but there is gPLUTO.hpp, which serves the same purpose, essentially. Now, the init argument list is incomplete. These parameters are still used by gPLUTO, but it's not sufficient. You need to add the run-config structure, which is essentially a way to overcome the fact that there are not so many global variables anymore. We pass this thing as a reference, okay, not as a pointer. So run-config always goes with the ampersand everywhere in the code, okay? This feature was not possible in C because C does not support references, but C++ does. For those of you who do not know what a reference is simple. It's a simple handle or an alias to a structure so that in the code, you can access argument of the structure simply with the dot as you were passing the structure by value, but that's not the case. So the reference is is as efficient as the pointer, but it has the advantage of preserving the name of the variable without introducing star in front of it. Right, so here we have the coordinate. US is the vector containing all the primitive variable, and that stays the same. There is no need to change it. We have not fixed the gamma here because this problem does not require the gamma. So the gamma is automatically fixed to be 5/3. But in case you would like to change it, it is a very simple way. Just do this, okay? So run config gamma is the same as the old G gamma, okay? It just is not as, there is no such a global variable because on GPU can create some problem maintaining all updating all the global variables, but in a structure is a different thing. Right. So that's essentially it as far as the init is concerned. Then we can move down. So there are a lot of things here that are not useful for us today. All the other functions inside your init CPP are the same one as PLUTO. One exception is the analysis, because in the old PLUTO, there was the const attribute here, which we have removed. So just remove const from analysis, otherwise it will not compile. While the const attribute remains, at least for now, in the user-defined boundary, but we don't have any user-defined. So that's the first thing to do. So as you can see, it's literally 3 lines, okay? It's a 30-second thing to be done. The definitions, this is still the old one, but it works also for the new version of gPLUTO for this particular case. And if it does not, the Python script will take care of it. We can do it now if you want. Okay, so I just need to export a different PLUTO here. Okay, so it's going to be gPLUTO for me. Okay, and I can set up the problem. I will keep everything to be the same. As you can see, it's again MHD, 2-dimension, Cartesian, linear, and second order Runge-Kutta. Ideal equation of state, constraint transport method. Okay, so the make file list is quite different from the old Pluto, but again, as the old Pluto, all make file are essentially, just hold on a second, all make file are listed in the config directory as it used to be before. For this particular case, I would actually need the new makefile because I want, well, okay, I'm going to use the Linux G++, though this does not contain the strong optimization directives, just a simple -o, but for now it will be enough. Okay, good. However, I cannot compile yet because I still need to do one modification. So definition is fine, init should be fine, but Pluto.ini is not, okay? So as I told you before, the way we handle the grid is different now. So we need to get rid of all these segments here because there is no the concept of segments or patch in gPLUTO, but just the grid from back to end. So in a certain way, it's actually much easier. Okay, so 0 is the initial point, sorry, the leftmost computational domain point. So 256 is the number of cells in that direction, in the x1, and this is essentially 2 pi, okay? And the same holds for the y direction. So Chombo refinement is not needed, so you can actually delete completely, and everything else stays the same. Okay, so I just deleted the Chombo thing because it will never be useful for our purposes. And I just modified the grid. So it's very important that you don't forget to modify the grid or the code will crash immediately at the first step. Right, so now I should be able to make. Let's make sure I have not forgot anything. It's another important thing that I'm not sure whether it was specified during the previous talk is the minus std C++17. So gPLUTO is written by using certain constructs that are possible only from C++ 2017 on. So don't use a compiler version which is earlier than 2017. Okay, so it's a standard. There is also a similar standard for C, if you want. That's just n minus std C17. Okay, if you're using a C compiler, if you want to compare with the older version of the code, which is written in C, but if you are sticking to gPLUTO, just use C++17. Okay, and now I can simply run the code. The output is a little bit scrambled because my terminal is narrow. Okay, looks better now. So as you can see, the diagnostic is a little bit more verbose than before, although this min and max can be removed. There is a macro to do that. So you can just keep the end step and the Mach number. But anyway, yeah, we are printing max and min. The reason for this is that during the development phase, when we were actually comparing the old Pluto with the new one, it was very useful to keep track of this maximum and minimum because sometimes GPU do not produce binary equal data, okay? Because mathematical operations are not done and executed in the same way as for the CPU. So it's likely that by running a problem on the GPU, you will get slightly different results. And this is particularly true if your problem has chaotic or turbulent behavior. So if you're running a simple 1D problem, maybe you will never notice the log file will be identical. But if you run like a jet problem, you know, with not a ballistic jet, but something that is under dense producing like wide cocoon, or any Kelvin-Helmholtz instability, or I mean anything that is unstable, Rayleigh-Taylor, Kelvin Helmholtz or whatever, then from some point on, the log file will start to differ, and there is nothing you can do about this, simply because the mathematics is different. This was actually complicating a little bit the porting, because it was difficult to have a reference file. So we did a lot of reference simulation on problems that were not presenting a chaotic behavior. Anyway, now we got the results. I can use IDL or whatever you prefer to display the data. Sorry, but it just went on my other monitor. That's it. So that's simply the Orson time produced with PLUTO. I can just make it done. So yeah, now I'm gonna show for reference the same thing, same resolution, same numerical scheme as for PLUTO. Just gonna change the title. Sorry, just give me a sec. Right, so you got PLUTO on the left, you have gPLUTO on the right. So there are marginally difference here, because this is a marginally chaotic problem, because essentially it's a double periodic vortex configuration, but the values are pretty much similar, okay? That can also change even within the code if you optimize slightly differently the code. There is also one other difference if you compare these two plots. Maybe I should do like a color plot. Let me see if I can get. Oh, sorry, I just misspelled it. No, probably this. Let's use a 33. Yes. So I want to show a couple of things. These are minor details, but may be useful. So if you see, the gPLUTO solution looks slightly better, because in PLUTO you can see tiny oscillations appearing here. But most likely the reason behind this behavior can be because the standard default limiter in PLUTO is a mixed combination of limiters, where the MC limiter is used for density, but pressure as min mod. While in gPLUTO, we don't allow for such mixed configuration, and there is a unique limiter for all variables. So I guess that if you play around with the limiter, you will probably get a better behavior. I mean, we can try and see, because I don't remember. See, there is no limiter being specified here. So if you care about obtaining exact, where even more similar, then you will need to adjust the limiter. We can just use one lim, okay, for PLUTO. And now I'm gonna do the same also for gPLUTO, but I think the default in gPLUTO is already one layer. However, let me check. Okay, so let's try now. So gPLUTO here is slightly slower because it has been compiled with the -O option, but usually it's competitive also with the other. Okay, let's run also the other one. Or I can, hold on, I can just change my config file and make it faster. Okay. Linux G++. Sorry, just give me a sec. Okay. There we go. So in the meantime, we can just go here, and so I got this toolbar. I don't know where I can put it. Maybe here. Okay. Okay, let me reload the data and replot. Okay, so as you can see now in PLUTO, those tiny little oscillations have disappeared because of the limiter. Now I think we're going to get pretty much the same result also in gPLUTO. Okay, it's gonna load again the data and display it. So yeah, as you can see now, if you look at this color scale, now we are exactly in the same range. Okay, PLUTO on the left, gPLUTO on the right. So this density for the final time step, I think we also have, I don't know if we have 2 time step. No, we don't. Okay. Anyway, is everything clear so far? Right, so we can proceed next and now dive into a much more complex setup, if you are okay. So I have chosen a setup that includes a different kind of physical ingredients, such as gravity, user-defined boundary conditions, geometry, and so on. So what I'm going to do, I'm just going to exit from my terminal here. And I'm going to delete completely my temporary directory in gPLUTO. Okay. Now, again, I have an empty directory to start a new migration. Again, I'm also going to close here IDL. Right. So the setup I have found for you is the disk planet. Roughly speaking, we have a Keplerian disk, and embedded inside the disk, there is a moving object that has a fixed gravitational potential. So the gravity is essentially given by 2 components, the central star, but also the planet. Okay, so it's nothing that you can model in by using a pointwise gravity, because both have their own influence on the surrounding disk. So everything is set in Keplerian motion using an isothermal equation of state. And yeah, I mean, gravity is prescribed using a potential rather than the body force because it's simple like that. So this is a standard test in the PLUTO directory. So what I'm going to do now, I'm just going to export again, just to be sure, because I have opened another terminal. So I'm going to set the PLUTO dir again to the old PLUTO. I'm working on my blue terminal here on the left. So I'm going to copy definitions 1, choosing the first configuration available with the distribution. That's it. So again, as before, I'm using PLUTO to compile this setup. So as you can see, we have hydro, it's 2D, it's polar geometry. So this is a very important thing if you are using geometries with PLUTO or gPLUTO. So there are a couple of things you must understand, because the word polar was a word chosen a long time ago, probably not in a very wise way, I should admit. But it was chosen to model the system of coordinate that goes like R, phi, Z in opposition to cylindrical, which was R, Z, and phi. However, this kind of double representation of the same coordinate system has been resolved in gPLUTO. In gPLUTO, we only have the word cylindrical. But in the old PLUTO, we still have either polar, spherical, or cylindrical. So this setup is polar, meaning that we are running a disk in 2D R phi coordinate, where R is the cylindrical radius and phi is the azimuthal coordinate. Okay. I insist this to be clear for everybody, okay? Because it can potentially lead to some misunderstanding if it is not clarified since the beginning. Now, body force is potential, and we can leave it like that. There is no cooling. Again, we use linear RK2. I mean, we can change this, but I mean, it's fine. Linear RK2 was the default, and we will keep it the way it was. So now we have 4 user-defined parameters that have already been pre-compiled, because again, this is a problem for the standard a PLUTO distribution. So everybody should be able to see exactly what I'm saying on my screen. Configuration 1 of disk planet. Now, the second menu is more specific to hydro, and we have dust fluid, isothermal equation of state, and we have rotating frame enabled, okay? And we will leave it like that. Rotating frame, for those of you who do not know what a rotating frame is an option that allows to solve the equation in a rotating frame of reference. This can be useful if you have a fast rotating object. You can just sit with the inner Keplerian orbit, and you know the inner part of the disk will be almost steady, you know, and you will see the outer part of the disk rotating faster. This has some advantages since the time step limitation comes mostly from the inner zone. Okay, so we will leave this as a yes. Now, the 4 parameters controlling this problem are the mass of the star, the mass of the disk, the mass of the planet, and then the viscosity, which, by the way, I don't think it's used in this particular configuration. So we will only be dealing with the mass of the star, mass of the disk, and mass of the planet. Right, so we can change the makefile and choose a simple Linux GCC, okay? So I can compile and run, but yeah, and we can run later. Okay, so before showing you the setup, I'm gonna do the usual copy. So I'm gonna take all my file like ini.c, eos.c, because an important thing I didn't say is that this particular problem is a spatially varying sound speed, meaning that the sound speed is changing with the radial position. Okay, so it's an isothermal equation of state. So the sound speed is constant, but it depends on the radius. Okay, so to speak, it doesn't depend on the thermodynamical variable. In that sense, it's a constant, but it's geometrically dependent on the radius. So we will keep this. Okay, and I will actually copy all the files to my temporary directory here. Okay, so that now I'm moving to the yellow terminal, okay? And in fact, I see these 4 files. Now, we will go ahead and rename those as we have done before, exactly the same way. So I'm gonna move ini.c into ini.cpp, that's first. Then I'm going to move definitions to definitions.hppe. Okay, and now I need to check because I don't remember what we did with the equation of state, because at some point, okay. So we needed to also rename eos.c. Actually, this file requires heavier modifications. So for now, I will leave it like this and show the equivalent recoded version, because that will take me more to be done. But it's actually quite simple. But the thing is that it's easier to modify another header file rather than rewriting this from scratch. Okay, so for now we will focus again on ini.cpp in definitions in PLUTO. So I'm going to open those 3 files. Right. Why doesn't see? Okay, so let's start from PLUTO. So ini.cpp. So this will take some time. Okay, so hopefully we should be able to finish by 4 o'clock. So just relax and take notes. Lucy, are you recording this session, right? I hope this is going to be recorded because, you know, it can be very instructive also for people to come. So, okay, so let's go. First thing, I need to modify my header files here. So it's going to be gPLUTO. Then second thing, as we already did for the Orstentang, I need to introduce the run config structure here as an argument. Now, if it's ideal, then G gamma here is replaced by run config gamma, very simply. Okay. Now, another thing, G input param. So G input param is something that in PLUTO is seen as global variables, but in gPLUTO, this array does not exist as a global variable, but rather is a member of the run config structure. So there is a very simple tweak for that, which is just declare at the very beginning of your init the pointer to param, which is going to contain a pointer to an array, which is input param. So input param replaces G input param. So the thing is that there is no G underscore, but it's a member of the run config structure. So that's quite easy to remember. Okay, now I should go ahead line by line and change all these input param to param simply because I have named that way. I could have renamed like pizza, okay, but I'm not gonna do that. So I prefer param. So a way to do that in Visual Studio Code, since that's the editor I'm using, I'm just gonna say that every time you find an instance of G input param, just replace it with param. So that's gonna make things faster. Okay, so I'm replacing all of them automatically just by clicking here. Done, done, done. All done. That's it. Okay. So, and the parameters are more or less taken care of. Another global variables, G underscore omega Z. Again, we don't have such a variable in gPLUTO, but rather we have omega Z as a member of the run config again. So what I'm going to do is just to name a local variable, okay, an automatic variable right here, so that I can get rid of this G, just not to get confused. Let me see where I have, okay, here, then I have it here. All right, that should be it for the init. So this is not what I wanted. So omega Z will be initialized to 0. So I can remove this define here. It's not necessary. Okay. Right. Okay, we can remove also the dust fluid option. There is no possibility to make that in PLUTO again. Right, so here we have an issue. Now, this is very important, so please follow me, especially if you are interested in doing non-Cartesian simulation with the code. So we don't have any things like polar geometry in the code, okay? We only have cylindrical. So cylindrical, let me write it here. gPLUTO only supports, and the plan is to go along that direction, okay? Cylindrical geometry. Cylindrical means R, phi, and Z. So cylindrical is the same as polar in the old PLUTO. Okay, so cylindrical and polar are the same, okay? Now some people may wonder, oh God, I am making jet simulation just by using R and Z. I don't care about phi because I am axis symmetric. So how should I do it? Don't worry, because gPLUTO can exclude automatically the intermediate direction. So just if you're using jet, you don't care about phi, which is not the case here, but if you to do that, you can exclude the direction. The same thing is in PLUTO, okay? So gPLUTO always uses cylindrical. It doesn't matter if you're doing a jet, it doesn't matter if you're doing a disk, but every time you are sticking to that coordinate system, cylindrical is the system that, does the job. So since gPLUTO does not understand the word polar, all we have to do here is to turn this into cylindrical, and that's it. Okay, nothing else. Now, omega Z has been computed here just in the case we have the rotating frame. However, I remember you that omega Z is a temporary variable. So we still need to copy it to the structure because it's not a global variable. So we need to make sure that that value is correctly reported also inside the structure. So you need to add a line like run config omega z equal to omega z. It is copy the local omega z into run config. So almost all global variables in PLUTO have a corresponding member in the run config structure. Okay, so I think we are pretty much done here. So if we're in 2-dimension, hold on, but there is no dependence on phi. So this problem is initializing everything using just the r coordinate. As you can see, there is a Keplerian velocity. Omega z is the velocity at which the rotating frame co-rotates. And it can be zero. If it is 0, then omega k is just a Keplerian velocity. And then we have a density profile. Right. So again, we should be done with the init, I guess. Well, the best way is to compile. The code will not compile, of course, but at least we'll see whether we got all our error somewhere else. See, geometry is turned to Cartesian because gPLUTO doesn't understand polar. So when it doesn't understand the keyword, it will automatically reset it to the first entry in the list, which is Cartesian. So let's just move to cylindrical, okay? Cylindrical geometry. Isothermal US rotating frame. So that's done. I can just simply choose Linux G++. All right, so I'm compiling. Then now at some point, the code will stop giving me lots of error. Here we are. So for example, G ISO sound speed. That's another global variable that we need to take care of. So that was at line 1. Okay, right here. See, I was forgetting this. Again, as you might have understood by now, the way to handle this is just to replace that with the run config ISO sound speed. Okay, and that because ISO sound speed is a member of the run config structure. Now it should be done. Let me see. Okay, now we have new errors, but they are coming from line 161, which is not in our init anymore. So the init function is completed, okay? Now we can move down in the setup. We can remove the const attribute from analysis as we did before. And now we can take care of the user-defined boundary, which will take us some time. So before we do this, let me just ask people, is everything clear so far? I mean, are you able to follow? Right, very good. Okay, so then I will continue, okay? Okay, let's continue. Now, the user-defined boundary, let's first of all see what it does and then how we should modify it. So this boundary is normalizing the density, by rescaling all the quantities in such a way that the integral is, I don't know, like 1 or pi. I didn't actually invent this setup. It was suggested a long time ago, probably more than 10 years ago. It's simply rescaling the density so that this integral is given the mass of the disk or something like that. But anyway, we don't really care about the mathematical operation in detail. What we care is how to translate these very same operations into something that gPLUTO can understand. Now, first thing is, of course, the grid. Now, the grid does not have a member called X. It has XC, because we also have X left and X right. Okay, so we use this second letter to identify which position in the cell you are referring to, and C stays for the center in logical space. Okay, so now I'm just simply making things more compact. I am defining my pointers to the grid. So this looks very much as the old PLUTO. except again that the name of the member is not X, but is XC with a capital C. But other than that, they are the same thing. Okay. Right. We will take care of the normalized density later. I prefer to start with the use-defined boundary condition. Let's have a look at what they do. So the boundary condition is rather simple to understand. So first of all, by default, all values are symmetrized with respect to the inner boundary. So 2I bag minus I minus 1 means that every index is mapped into the mirror one with respect to the inner accretion border. Okay, this is something most of you may have already seen. So I bag is mapped into I bag minus 1, and I bag minus 1 is mapped into I bag, and so on. Then the sign of the radial velocity is reversed so that it effectively acts as a reflective, like a wall. Okay, then we have the coordinates here. That is this. We always want to have the cylindrical radius. So this is easy for polar, which by the way has to become cylindrical now. While in spherical coordinate is gonna be r times the sine of theta. Right, then V phi is kept constant to the original value, so we don't allow actually V phi to be symmetrized, or better, I mean, we overwrite the previous value with this new one. Okay, we do a similar thing with Fargo because Fargo solves the equation ring by ring by decomposing the total velocity into a deviation plus a background motion. So the background motion is solved separately therefore what you see here is only the residual, which must be kept to 0. We don't care about dust fluid at the moment, so we can remove these lines. Okay, but unfortunately, the way this piece of code is written will never work in gPLUTO. There are essentially, it has to be changed. So the first thing is that we don't have macros such as X1 bag, X1 end. So all these have been completely removed from the code. All we have is the DOM loop macro, the box loop macro, okay, which is actually quite powerful and can handle all specific situation. So the box loop is, but this is, okay, this was present already also in the earlier code version. I mean, the box is not a new thing. It's present also in PLUTO, but some of the setups like this one were not changed, and so they kept a very old macro, okay? In fact, the box is a standard argument to the user-defined boundary. It's not something we invented for gPLUTO. It was there already. We just decided to empower it. Right, so we have the box loop with ijk. Keep in mind that now all the loops are ijk everywhere, okay? So we don't need to pay attention to reversing index. So this thing doesn't really go the way it's written, okay? But it has to be replaced. So I'm commenting the old one, I'm rewriting the new one. So the new syntax is, as I showed before, ijk and v. Okay, it's just a replacement for that. And here we should have first two I bag, jk, and v. However, I bag in gPLUTO was a global index that was identified the first active cell in the I direction. We don't have such index convention anymore because, again, those are global variables. But that's very easy to replace because you can just define at the beginning, this is the same as the L bag member of the grid structure. Okay, so same as old I bag. And of course, we have exactly the same index also for the end, which is a replacement for the old I end. Okay. So now here you just replace it with I bag minus I minus 1. Okay. Right. Now, again, we should fix all these square bracket with the more convenient notation, ij, k, and v. So here we go with ijk vx1. The same here. So just go for ijk iv5. Same for the line below. Same here. So this is actually the other boundary, the x1 end. So again, also here we need to fix the box loop. So it's just going to be box ijk. Right? So here again, we don't have in the capital, but we have the local in, which does exactly the same thing. Again, there is no such a thing as polar geometry. Let's switch it to cylindrical. Just putting empty spaces to make this more clear. Yeah, there is some mess here with the spherical grid. We can just do it like that. Okay, and then remove all these square brackets. Same here. You know, it takes some time, but it's not complicated, trust me. I mean, once you understand it, it's a 30-minute thing in the worst case. I'm going slower because I am explaining you, but keep also in mind that many of these configurations have been already ported to gPLUTO, so we have done the work for you. No need for dust fluid anymore. Right, okay. So in principle, my routine should be pretty much okay. If I'm sure I'm okay. G omega Z. Here we go. Yeah, okay. So now we need to use the omega Z variable, which is a global variable, but we don't have such a global variable. So how do we address the situation? Well, the best way is to, again, define a local one, which will contain a copy of the run config. But there is no run config here. Well, there is actually, because run config is a member of the data structure. So wherever data arrives, then omega Z is also available. Okay, so we just do it like that. So this is the copy. We copy from the structure to a local variable. And then we just remove the G underscore. The same goes here. And that should have fixed all the issues for the user-defined boundary. Let's see if...
Sorry, you have one parameter that is not needed in line 191. You don't need that in Wizard.
Yeah. There is an extra NV. Thank you. Thank you for spotting that. Yeah. Thank you. Okay. So if we now make, okay, we have some extra error. Let's see where they are coming from. Yeah, sorry, that's my mistake. Box is already a pointer, so there is no need to take its address with the ampersand operator. That's my fault. Okay, then the next error is at line 229. So then let me scroll down. So we are in a different function. The function is normalized density, is the function that rescales everything. So essentially it multiplies everything by this, okay? And we also have to take care about the units. So this is something we did not mention in our presentation, but I'm gonna do it today. Because again, so these units were macros in the old version of the code, but they are variables inside the structure in the new version of the code. So I'm going to take some time now to explain how we can port this normalized density. So the first thing is that so there is a loop here, DOM loop, which does not exist in gPLUTO anymore. But so all you have to do is to define a box here that contains the computational domain. So The way we do it is just define a local box, okay? And then there is a simple constructor for this box, which I'm gonna show in a minute. Just hold on. Okay, so we can simply do our box define from grid lbag to grid lend using box. So this is a definition of the box. It will immediately construct a box that starts from bag to end, which is in fact the computational domain. lbag and lend are the local index on the processor. So this is the different, I mean, each processor will see a different portion of the domain, but the way the processor loops over those cells is done by this box, okay? Keep in mind that the box definition can be done also by calling our box by explicitly assigning all the index, and this is possible because C++ allows polymorphism, which means you can have two different functions with the same name, but only varying in the number of arguments. In fact, if you go inside gPLUTO and you look at the R box, you will see that there are two ways of defining such a box. One is the R box define this version, which takes 6 integers plus a pointer to the box. But there is also the shorter way, which is just by using 2 pointers to integers and then the R box. So they do the same job. It depends which of the two is more convenient for you, okay? In this case, since I want to define a domain from the grid, it's way more convenient to define the second one, to use the second one, okay? While we leave the other one to more specific purposes. Right, so this is done. Now, let's, okay, param. We don't have param at the moment, okay? Because, no, we just changed it before. Remember when I do the edit, search, and replace? So this is being replaced since that time. So, but I can quickly recover param by doing double param is equal to d, run config, input param. Okay, I can just work it that way. That should be okay. Then my DOM loop will be transformed into a box loop running on the address of the box, ijk. Okay, and then those will become simply ijk row. And the same holds for pressure, so I can leave DVC, but here we'll have ijk and pressure. Okay. Right. And then let's keep compiling. Okay. This is compiled. Now we have an error at line 3.114, which is a different function. It is actually the body force function. So this will take more than 10 minutes. So since we have a coffee break at 4, I would rather suggest a slightly different alternative. Why don't we start the coffee break right now? And then we anticipate by 10 minutes our session, you know, because we are supposed to be back at 4:15. Okay, so, but if we start the coffee break now, then we can recover at 4:05 and finish slightly earlier, if everybody agrees. It's just because this session will take me more than 10 minutes and I don't like interrupting, you know, things that are quite demanding in terms of effort. Is everybody okay with this strategy? Yeah, okay. So let's do the coffee break now, and then in 15 minutes, we'll convey again and keep going on modifying the gravity potential, okay? Thank you. We'll see you in a bit. Okay, so the last step we need to take is to convert this function, well, actually only the second one, but since we are at it, we can also discuss how we change the implementation of the body force, because the prototype of this function has changed. Okay, now I'm gonna show you what is the new prototype. So for the first one, it's slightly different. Well, slightly, it's completely different, to be honest. So the new prototype is this one. Okay, so the name stays the same, but the argument list is completely different. So we have a state. So as I was saying, sorry, this is the, let me start again. Body force vector and body force potential. So these two functions have to be modified. And as I was saying, the prototype is different. So that's the new prototype. As you can see, the list contains only 3 arguments, which are state and run config and the gravity vector in the end. So all the information concerning position, coordinates are all embedded in this structure. So it's quite a powerful way to communicate with the rest of the code. So we will delete the previous one, and we do the same thing also for the potential. I'm just copying and pasting from another terminal. That's it, okay? So also the body force potential has exactly the same parameter list as the body force vector. So therefore we can delete the old one and rely on state. Okay, so now the first thing is, how do we get the coordinate back? Okay, and the way to do this is just to write here const double or even just without the const probably x1. Okay, so that's the first coordinate is contained in state x1, and the same is true for the other coordinates. So just a simple copy. So they are passed through state because state contains also several other information that may be useful at this stage. Then of course, this function here, you see there is a lot to be done here. For example, the parameter are contained here, but again, we also have the parameter because run config does the job of replacing global variables. So again, we will simply do const double param equal to run config input param. Okay, and that's the second step. Okay, now let's scroll down. So we have polar here, and then we will just switch it to cylindrical as usual. Everything stays the same. In this piece of code, we are just mapping all the x1, x2, and x3 to r, phi, and z where necessary, defining. So that's the cylindrical radius, that's the spherical radius, but we are working in cylindrical at the moment. So yeah, in 2 dimensions, so only this piece of code will be actually compiled. We don't have any vertical extension, so we can ignore this. Then everything here stays more or less the same. X and Y are the equivalent Cartesian coordinate. Those two were already present since before, so we leave those as they were. There is nothing to be done here. Okay, now we need to define the position of the planet, which is given by these xp and yp coordinates. So P stands for planet. There are a number of things to be done here. For example, the first one is that omega z, omega z can remain the same because I don't remember why this is computed again, but it was done also in PLUTO, so we won't change this because it's the same one. I don't remember why we kept a second definition of omega z, but that should be the same as the previous one, right? Yeah. Anyway, we leave it that way. One important thing is the time, and as you can see here on line 302 and 303, we have a reference to 2 time information. One is the simulation time, and the other one is the increment with g dt. So g time is simply replaced by run config time. And And this, yes, okay, I'm not sure. So this was can be commented at this time. The reason is that I'm not sure whether GDT has been incorporated inside run config, but that's a minor adjustment. We can probably skip that at the moment. I'm going to double check later about this. I don't remember exactly why GDT has been commented. So everything then goes the same. Let me check later. Okay, and this is done. So one thing that we forgot is the definition of this unit. Okay, so I'm going to spend a few words about how these units must be redefined. So we don't have this macro in the code, but what we do have are the, okay, so let me just see. So in the old version of the code, the unit, length, density, and velocity were macro specified in your definitions.hpp. This is not possible anymore, not in this way. So what we do is that we cut those from definitions and define exactly the same thing right here. So what we can do here is just transform here, just add a comment, okay? Define CGS units, okay? And unit length as a macro as a corresponding redefinition in run config unit length, lowercase. Okay, and that's the way we can do it. Same for density. It's unit density, lowercase. Okay, but we have unit length here, so when we could replicate a run config unit length 3 times, but it's going to be expensive, so it's better if we just define u length to be, let me just use a temporary variable to make the code easier to read, okay? So I'm going to define unit density using local variables and then copy those. Or simply, maybe I can just use unit length. So this is going to be UL. And now that I have UL, this, you see here is a length cube because it's unit length times unit length times unit length. So just replace with UL like that. Okay. Then we also have the same thing with the unit velocity. So it's again run config unit velocity. And that's going to be const, and then we have UL. Okay. So it's not G input param, but it's simple param because we have defined that in this way. See, the advantage of using not a macro, but a variable is, I mean, there are several advantages, but the most notable one is that we don't need to define a macro that incorporates global variables. Because see, this is a literal substitution, so you can make the code slightly slower. But if we compute it as a number, then it will be done just once in init. So it's going to be kept like this. Okay, that should be solve the issue. Now, once we go back into this function where we were using all the 3 units, okay, then we can simply define, for example, here, double unit length equal to run config unit length. And we can do unit density also, run config unit density. And then here, just use UD times UL times UL times UL. So the MC is divided by density times length cube, which becomes this unit. And that's pretty much it. Let's see if the code compiles now. I may have left something out. Okay, so 236, 236. Yeah, sorry. We need to do like that because we don't pass run config directly. We use simply D, but run config is a parameter of D. In alternative, you may want to modify this since this is not a PLUTO standard function, but is a function introduced for this problem only. You can add the run config structure here, but you know, there is no need to do that since it's already a member of the data structure. So let's see now. Okay, as you see, compilation is now successful. Okay. Now, last thing before we hit run, it's just here, PLUTO.ini has to be modified. So again, we remove the division in patches. So there is no distinction between patches, just a single grid. Again, remove the Chombo refinement. I mean, if you forget to remove Chombo refinement, it's not a big deal since this section of this file are completely ignored by PLUTO, okay? And that should be it, I guess. So let's see, we can run it on PLUTO. And we can run it in gPLUTO as well. Yeah. So hopefully I should have fixed everything. Let's wait a few minutes while the code integrates. In the meantime, I can take questions.
Previously you said that we also need to modify the equation of state for...
Yes, that's a good point. Yes. Okay, actually, that's a very good point. Thank you for remembering me that because I was forgetting about this. So, yeah, so let's stop it for a minute. Yeah, that's a good point, the equation of state. So what I'm going to do now, I'm going to copy directly the file that I already modified a few months ago. Oh my God, it's not included. It's too bad. So I should fix this in the distribution. There is no HPP. I'm going to take from the development, then I'm going to fix the problem later. So let me compare both the old PLUTO and the new gPLUTO file. So in the old PLUTO, which is the one you're looking at on my screen, so there was this file called eos.c that was part of your local directory because in this file, some modifications were necessary. So for example, here we were introducing, you know, this modification. So the sound speed A2, which is member of this P structure, P is a state, depends on radius, okay? And this modification was done essentially for all three directions, okay? And the file eos.c contains, besides sound speed squared, contains also enthalpy, entropy, etc. However, in gPLUTO, we have done things slightly easier than that. So we provide the same functions, but they are inlined and they are preceded with this pragma CC routine sec, which instructs the OpenACC model that this routine has to be sequentially executed on each thread. This is not necessary if you're running on CPU. You don't care about this on CPU, only on GPUs, but this is already there. So the modifications, as you can see, we have again enthalpy, entropy, and sound speed too. Now, this is much easier if you compare the two files. I mean, the old PLUTO was a little bit cumbersome because you had to define all this position, phase center, etc., because those functions were handling an entire row of values at a time, while the inline function are doing a single cell at a time. So in fact, one advantage of gPLUTO is that there are only two types of function acting on a single purpose. So they are either the entire computational domain, in which case we call them kernels because they are done within a box loop, or they are cell by cell. There is no such a thing as doing one direction at a time, maybe only except for a very isolated cases, but we never use a construct that does only one row of data. It's either all the computational domain or a single cell. And in fact, as you can see, this is much shorter, right? Because you just say, okay, state A2 is it's isothermal, so we use a sound speed as on the numerator, whereas on the actual square, we divide by r by simply using the state. So state will give you the coordinates at the point where the code expects that entity to be computed. So it can be a phase quantity, it can be a center quantity, but you don't care. I mean, you don't need to distinguish between a phase center or a cell center. It doesn't matter. It's just state. Whatever it's in state is fine because we take care of this earlier than this function. So all you have to do is just divide this by r. Okay, but it's an HPP. So I'm also taking this opportunity to clarify between, CPP and HPP. So HPP files are usually used for header, as you may have understood now, such as definitions.hpp. But there are cases where you need to introduce inline functions. So an inline function means that the code takes the content of that functions and insert the content right where it is called. It's similar to macro in a way, but they allow you to define function. Of course, the compiler is free to ignore the inline because inline is not forcing the compiler to inline the function, but it gives a strong suggestion to do that. And if the function is not extremely long and if it does not contain lots of parameters, usually the compiler is happy to satisfy your need and will insert this directly inside. So all we need to care, of course, is just the physics hydro or MHD because this problem doesn't work for relativistic flows. So this is just copied from there, okay? And just you leave it like that. So in that case, your EOS.c can be simply deleted, okay? We can delete EOS.c because there is no such a function and it was easier to replace to modify the template. You may find this function, right? I think it's right in the main source directory. Yeah, it's here. By the way, I'm not sure whether we discussed where files are located, but since we are here, I can take the chance and just show you very briefly where we are, how the SRC directory organized. So it's similar to the old one, except that there is no time stepping subfolder, sorry, because everything is done by a single function here. But you still can see the Fargo, HD, MHD, I mean, all the subdirectory that are pertaining to explicit modules are actually here, okay? So that should be fine. Now let me run a simulation again. In the meantime, we can display the data. So let's go with PLUTO. So PLUTO has finished the computation. It did like 6,000 steps. Now I can load the data and I can display. So I'm using IDL, but later on during the practice session, we will also use GNU plot and PyPLUTO or visit for more complex data. Okay, so in IDL, I can easily go for a plot by using the polar keyword. Yeah, hold on, that it's showing on my other screen. Okay, right here. So let me just do the image larger, put in the title, and adding a vertical bar. Okay. Maybe also add a color. Okay, so this is PLUTO. Now I'm gonna wait for gPLUTO to finish. It's gonna take some time, but anyway, I think we should recover a very similar result. In the meantime, let me know if you have other questions. So if there are no questions, while we are waiting for the integration to finish, I would like to show you what I was mentioning before. So all functions are working in kernel. So let me take a Riemann solver so that we make things easier. So let me take the HLL or the Hydro module. So Marco mentioned this. We're using function templates. So what this means is the following. So it will create from a single function 3 different functions, one per direction, based on this template parameter. This is a classical C++ feature, and it allows you to obtain, let's say, similar copy of the function, but by varying one parameter. As you can see, this function operates on the entire domain because it has this nested loop, while in the previous version of the code, you were doing row by row, okay? But in order to exploit GPU better, it's much more convenient to overhead the CPU as much as possible by doing lots of data to process in a single kernel, rather than replicating many one-dimensional kernels. So these are simply pointer offset, and the rest of the function shares several similarities with the previous version of the code. We are also trying to do our best to comment the code, so it should not be too difficult to understand. Also, we keep a very similar structure for this function for all other Riemann solver. I mean, you can go and dive into a much more complex Riemann solver, such as the HLD for the relativistic module. And as you can see, we also have, 3 nested loop here, etc., etc. Okay. One thing, since I'm here and we are waiting for the integration to finish, we are already 60%. So errors are printed, if there is any, at the end of the kernel by specifying the where directory, with the where function. The where function takes the name from which the function was called, the kernel error, the box, the grid, and the data. So all the information is contained inside dr. dr is handling all the errors that are being collected during this single kernel. So if an error is raised, this variable is being updated with the code error and the cell location, and it is reported only at the end. This is necessary because you don't want to use print statement inside an accelerated loop, okay? Because it will slow down the code enormously. So don't do that, okay? It took us some time to come up with this strategy, but it works fairly well, actually. And there are also different levels of verbosity inside gPLUTO. You can just print that an error occurred, or you can print what kind of error, you can print exactly the cell, the name of the error, etc., etc. There are, I think, 3 levels of verbosity possible. Okay, let's wait. It's almost done. Okay, so let's see if we got the same result. Hopefully, yes. Take from here. Yeah, not done. So that's gPLUTO. Oops. Okay. So again, Pluto on the left, gPLUTO on the right, and you can see the value are pretty much the same. Actually, yeah, they are not exactly overlapping, but to 2 decimal digits, they look identical. Okay, so was this clear enough? I hope so. Yeah, of course you have to manage. I mean, this was a very complicated setup. I mean, as you saw, the Orstand tank took, I mean, literally speaking, probably less than 5 minutes, even, 1 minute. There were 3 lines to be modified. But for the more complex setup where you have user-defined boundary condition or complicated gravity assignment, it takes some more time. But the code again will contain many other examples from which you can take inspiration. Okay. Okay, so I see, Lucy, you have to leave earlier. It's fine, no problem. So this session is finished. We have still some time. If you are not too tired, we can proceed with the very first practice session, which is a one on a shock cube. What do you think? I mean, we still have plenty of time tomorrow as well, okay? That depends on you.
Yeah, thank you, Abra. I just want to add that I will now stop recording because the hands-on sessions of this workshop are not recorded. And once again, thank you for great lectures, you and all your PLUTO team. And also thank you, participants, for attending. And just wish you have a nice rest of the day and hopefully see you soon on our future events and courses. Thank you. Bye.